Good morning, Professor John.
Good morning.
I think many of the students or candidates has joined. So you can start your session, sir.
Okay. All right. Okay, then I will start. So first of all, good morning to all of you. So this is the last day. Congratulations to everyone who made it till now. And what we're going to do today are two things. I would like to spend an hour or an hour and a half talking about an algorithm, a Bayesian algorithm called the approximate message passing algorithm. It's a very important class of algorithms which are rooted in physics and communication, and which are often, let's say, the best algorithm you can imagine for a given problem. If it's, let's say, it applies to certain types of problems, but when applicable, it's usually the best algorithm we know. So it defines what we call the algorithmic limits, in the sense that we don't know any efficient algorithms that can beat this one, and so therefore it's really the one that defines the algorithmic phase transition. And usually the gap between the performance of the minimum mean square estimator, the base optimal performance, and this AMP algorithm is what we call the statistical to computational gap, which was the hard phase, which I also call the hard phase at the beginning of the course. So that's why it's so important, not because it defines this algorithmic hardness. So it's very important. Not only it's important for applications, but also it's very important from the theoretical perspective, because it's an algorithm you can rigorously analyze. And so by understanding its behavior, you can say many things about the problem. And then I will not derive completely the algorithm. I will just give you some ideas of what it is. And then I will spend the rest of the time to show to you a presentation that I had prepared for another event, which is about large number of applications of these techniques, and importantly the connections between statistical physics and information processing systems. Okay, let me just open one thing that I need. My phone. Excuse me, just give me 1 second. Okay. Yes. Okay. Right. So let's start. So let's say introduction to the approximate message passing algorithm, and also doing so I will introduce another connected algorithm which is called belief propagation. So from what I understood, many of you are coming from electrical engineering or communication background, if I'm not mistaken. If that's the case, you probably have heard about belief propagation. It's also called the max or the sum product algorithm. It's one of the most important error correcting algorithm. It's a decoder that is used in modern communications a lot. And so, yeah. Okay, so let's start by recalling what's the goal that I want to why do we study this algorithm? Because if we go back to this picture here, there was three curves. There was the MMSE, which we have analyzed yesterday using the replica method. There was the spectral PCA, which we have analyzed the second day using random matrix theory. And there is this third curve, which is matching the minimum mean square estimator on the algorithmically easy regime and the impossible regime, not in the algorithmically hard phase. And this is this approximate message passing algorithm. So I want to tell you what it is. And this type of algorithmically hard phases, computer scientists call this statistical to computational gaps. So you see, because you have a gap between, in this region, you have a gap between what you can statistically achieve, so independently of the computational power you already spend, and if you fix yourself a computational constraint and you want efficiency, you can only reach that performance. So you have a gap between statistical and computational performance, okay? Computationally efficient performance. Perfect. Okay. So the first thing I'm going to do is present belief propagation. So we will see that this algorithm that, again, I think some of you have encountered is actually the approximate message passing algorithm in this quiz, in the sense that belief propagation is an algorithm which is used to solve inference problems on sparse graphs. Approximate message passing is just writing the belief propagation equations and applying them to a dense graph of like the Wigner spike model is, and doing some kind of central limit type of approximations to simplify the equations. So let me explain what I mean by this. So the first notion, so belief propagation is an algorithm that is used to perform inference on a factor graph. So what is a factor graph? Inference for factor graphs. So a factor graph is just a graphical way to represent certain types of probability distributions, which is very general, which are just probability distribution that can be written in a factorized manner. So that's why it's called factor graph. So let's say you have a probability distribution over X. It may depend on some parameters theta. Let's say the data in an inference problem, the measured data. If this is a posterior, this would be conditioned on the data. So this is 1 over a normalization, and it's a product over A. So A is indexing the factors, not the replicas like yesterday. We're not talking about the replica method now. These are factors, which are just functions, psi A, of a subset of variables, xa, and that depend on one on parameters theta A. So XA is a subset of variables, XA1, XA cardinal of A. It has a certain cardinal, so maybe there is one variable in it, maybe there are 2, 3, 4, 10, it can be any number. It's just a subset of the original variables, okay? Subset of components of the original vector X, okay? Perfect. These psi A's are called compatibility functions or constraints. And they're non-negative. Compatibility or constraints, okay, or just factors. Perfect. So
I had a question.
Yes.
So when you mean a factor graph, a graph as in like a graph in the mathematical sense, like nodes with lines?
Yeah, exactly, nodes and lines. Because once you have a probability distribution like this, I can represent it as a graph, as nodes and lines. Let me do it. So the factor graph associated with this probability distribution would be the following one. So I would place a node for every variable. So this would be X that enters my probability distribution. Okay. And each time in this distribution there is a factor, a function here that depends on a certain subset of these variables, of these nodes, then I draw a box and I connect these nodes to this box. So let's say this would be a psi, and let me index it by the nodes to which it's connected. This would be a psi 2, 3, 4, which is any non-negative function of x2, x3, and x4. And it may also depend on some additional parameters. That could be data, that could be anything. That could be also a random variable itself. Okay, so this is a factor. I could have a factor there. This would be a psi 1, 2. I could have a single factor there. So this means it's a function of psi 3 only. And so on.
So okay. Are the factors, are they like hyper edges?
Yes, they're hyper edges, exactly.
Yes. Okay. Yeah, also excuse me for not showing the camera, it's early.
Yeah, and thank you for being there and proactive, actually. Thanks, Joe.
Next session.
Yes. So yes, these are hyper edges. So these are hyper edges in a hypergraph. Yeah. Perfect. Okay, so this is so you can think equivalently of this graphical representation or as this probability distribution. They encode the same information. So if you know this graph, if I give you this graph, you can write the associated distribution and vice versa. Okay. So once you have a graph like this, to write down the probability distribution, it's very simple. You take all the factors, all the boxes, and you make a product over them, and then you normalize. So this 1 over this v is just the sum over all values of x of this product of factors. Okay? So you have equivalence between the two. Perfect. So now that we have a notion of factor graph, what's the task? It's to perform marginalization. So we want to do inference, and to do inference, we do that through marginalization. So it means that given the joint law of all the x's, okay, I will emphasize that it's a big vector here, I will drop the dependence on theta, okay, but this law again can depend on some additional parameters. The goal is to obtain the marginals. Let's say there are n variables. Okay. Because once you have marginals, you can make decisions. Okay, so for example, the Bayesian optimal estimator, you remember the x base, which is the posterior mean, given the data. This is really the vector of marginal means. X1 given y, xn given y. And these are the expectations. This is the integral with respect to p x1 of x1 dx1 and so on. So you see, if I have access to the marginals, I can compute Bayesian estimators, and I can also compute the MAP estimator, the maximum a posteriori. Okay, I can maximize the marginal for every component, and so on and so forth. So I can make decisions which can be optimal. Okay, so this is really the goal: is to go from the joint distribution to the marginals in order to perform inference. Okay, so belief propagation is an efficient way to compute the marginals on rather generic factor graphs.
So when you say make a decision, what do you mean? Choose a certain variable?
Yeah, choose a value for the variables. So for example, if we're talking about an inference problem, the factor graph would be a posterior distribution, and these thetas would represent the observed data. Okay. In this case, you would like to extract an estimator for these unknown parameters. Okay, and so you would like to compute, let's say, the posterior mean, the minimum mean square estimator, which is the vector of marginal means, right? It means you need the marginals. But you can also do that. You can use that in a combinatorial optimization problem. Let's say you want to minimize a complicated function. This function is parameterized by a big vector, and you have constraints that between these variables represented by these factors. For example, the coloring problem, which is a hard combinatorial optimization problem, tells you that if two nodes are connected, then they cannot take the same color. Okay, so let's say you have 4 possible colors, so 4 possible values for each variable, and you are enforcing that if two variables are connected by an edge like this, they cannot take the same color.
Yes.
And you're looking for configurations of the x's that verify this. It's called a coloring. Then what you need to do is to obtain the marginals, and then what you're going to do is to attribute every node. You're going to select the color of every node according to the marginal. You're going to take the maximum of the marginal for every node. It's the maximum a posteriori estimator for every node. Okay, it's again an inference problem, but in the context of combinatorial optimization. Is it clear?
Yes.
In this case, the probability. So if you have a combinatorial optimization problem, these factors would be 0 if the two nodes are of the same color, in which case the probability would be 0. As soon as you have one error, one constraint which is not verified, this measure is 0. And otherwise it is 1. For any other choice, it's 1. So you are looking for these colorings such that and this probability distribution would kind of weight uniformly all these colorings. And any other choices would have 0 measure. And you're trying to sample this measure. It's the same. Okay.
Yeah, it's the coloring problem is very similar to the like a POTS model.
Yeah, it's a possible. It's the same. Yeah.
Yeah.
I'm saying coloring because maybe for non-physicists but of course you can also think of this as error correcting codes. These constraints would be let's say could be parity checks between bits. This would be bits, binary variables, and one factor like this would be a parity check. It would enforce that the sum of these two bits is a even number, for example. And so you are constructing a code like this. And then you receive a noisy version of those parity bits, and you try to reconstruct them. And so what you're going to do is to run belief propagation. You're going to try to sample to find configurations that are in agreement with all these these parity checks, and this is decoding. Okay, you are decoding. Okay. So actually, this belief propagation I'm going to write was discovered. It is really at the core of two communities. It was discovered by Gallagher in the 60s in the context of error correcting codes. He was an engineer, and it was also discovered independently, let's say in the 70s, in the context of spin glasses. So it's what we call in physics the cavity equations. It's the same. Okay. And it's one of the main tools to study spin glasses and spin models in general. Okay, so let me try to write these equations. Okay. But really, the goal is to solve this problem. It's the marginalization problem. You have a joint distribution, and you want to look at to compute marginals. So of course, computing the marginal directly in general is a hard problem, right? And that's why you need an efficient way to do it. Because if I want to compute, let's say, P of x1, I need to integrate over all the variables but the first of the joint loop. And this has, in general, a volume Rn minus 1. So it's a very high dimensional integral, right? So I cannot compute it. So you need an efficient way to do so, and that's where belief propagation enters into the... Perfect. So let me directly write the equations and then discuss them. So belief propagation. So for I equal 1 to n, the number of variables, and a equal 1 to m, the number of factors, I'm going to define two types of so-called messages, which are themselves probability distributions. They are the factor to nodes messages at time t that depends on xi, which is equal to 1 over a normalization of the integral of the factor psi a that depends on this set of nodes to which it is connected, product of all the nodes j connected to the factor a. So this notation means the neighborhood of a except the node I. Okay. And then I look at all these nodes. They're sending themselves messages towards A without a hat. It's the other type of message. These are with a hat. So these are factor to node messages. These are nodes to factor messages of xj at time t, and I integrate the xj. And then the node to factor message, which also depends on I and in which is a well-normalized probability distribution, is just the product over all the factors B that are connected to I in the neighborhood of I, but factor A. And I look at all the information sent by these factors to xi. Okay? So locally, if you want, you have you have, you can think of, so the first, let me move this and make drawings. The first type of messages, so it's a factor to node, which is connected to other factors, and this factor is connected to other nodes, okay, and so on. So this is the node I, which is receiving the message. This is the factor A, which is a box, and we're looking at the message sent from A to I. What is it? It is just the product of the messages that are going towards this factor from the other nodes to which it's connected. These are these guys here. But I'm not considering the one coming from I, because I'm sending to I. So I'm making the product. You should think of this as kind of marginals. Marginals, the best, so I will give you the meaning more precisely, but these are probability distributions. And then I'm like integrating out these marginals against this factor in order to obtain something that depends only on xi. Okay, so I take this function, I integrate out these variables according to these probability distributions, and I obtain something that depends on xi only. So what's the meaning of this quantity? It's called also a cavity distribution, because what I'm doing is like I'm doing a cavity in the sense that I'm cutting this edge there, as if this factor was only connected to these nodes here, but not that one. And I'm looking at what is the information that this factor only sends to this node. So it's like if I was, sorry, it's like if I was cutting there. Said a mistake. As if I was cutting this edge there. So this node, from when computing this thing here, it's as if it was only connected to this factor. So I'm disconnecting to all the rest of the graph there. And I'm looking at what's the marginal distribution of this node in this modified graph where all this part has been removed. And I'm only considering this part of the graph, okay? And in this case, its marginal distribution is indeed given exactly by this. This is correct. You see, because if there is no other part there, the only connection from this node to the rest of the graph is through this factor. And in this case, this equation is exact. Okay, so I'm digging a cavity or cutting an edge, removing all this, and computing the marginal distribution of this node in this remaining graph, which we call also the cavity graph. Now, what is this message here? So I have a node, still node I, that is sending information to factor A, which is itself connected to other nodes. And this node is connected to other factors, which are connected to other nodes. So what I'm doing, yes.
Oh, sorry. Yeah, I was thinking, so the message passing, the M, it seems to resemble some sort of incidence matrix, like from edges to nodes.
Yeah, I mean, which A is sending to which I and vice versa is related to the adjacency matrix of the graph. Yeah, the adjacency
the incidence. Yeah, so the incidence is mapping the nodes to the edges, and so if we have A as edges,
yeah,
okay, yeah. Of course, when you take the matrix product, you get the adjacency matrix, but.
Okay, yeah, you're probably right.
Oh, okay. I'm not sure. Yeah, I'm not sure. So M in practice is an array of numbers. Like if
no,
you
M.
Actually...
No. M really. This is a probability distribution. This is a normalized probability.
Hmm.
It's a number between 0 and 1 for every xi. So it tells you what's the probability to take the value xi for the variable x.
Okay. Normalized probability. Okay.
Yeah, it's a well-defined probability distribution. So this is a normalization.
I see. Yes.
Okay, so this z here is the integration of this with respect to xi as well. So that the integral of this object with respect to xi is 1.
Exactly.
Okay.
So if M is a matrix, let's say with index A and I, if you sum over I, it should be 1.
Yeah. Yes, you're right. You're
Okay.
correct. No. You don't sum over I. You sum over x. So I is fixed, and you sum over the values of xi. So let's say if we're working with binary variables, let's say bits, the sum of this with xi equals 0 or 1 is 1. Xi is the argument for a given I. Okay, you're not summing over I.
I see.
Okay.
I see. Okay.
Thanks for the clarifications. So now the other messages, what they are. So the message from I to A is the product of the messages coming from the other factors. You just make a product to send this one without considering the one coming in that direction. So it's as if you're creating a chaotic graph by cutting here. Now you're saying, what's the probability distribution? This object is the probability distribution of I in a graph where this edge would not be present. So it would be connected to all the factors that it is connected to in the original graph, but this one.
So
here
the messages from I to A should be the sum of the messages, or either sum or product.
No, it's a product.
So once it is a product and we are dealing with the binary thing, then the result will be 0.
So the result will be 0 if what?
Sending the binary messages either in the form of 1 or 0.
No. These messages are not binary. So let's say when I said binary, I meant the argument can be binary. But still, this would be a probability distribution for a binary variable. So it's still a number between 0 and 1. Okay? But these numbers some of them could be 0. Then the output is 0. It means that, so for example, if this constraint is telling you that some value can be
the product, the output will be 0.
Yeah, it can be, the product can be 0. If one of these messages is 0 or there, the resulting message there is 0 as well.
If the product is 0, then loss of information will be there in the channel.
No, because if you think in terms of coding, the observations from the channels have been obtained, and now you are just doing you are the inference step, you are the decoding step. So it's not so the communication has been done already, and now given the data, you're trying to decode the bits. Okay, and so depending on what's the communication channel, the model for the noise, etc., some sequence of bits have a non-zero probability to have been transmitted given the noisy observations that you got from the channel. Some have 0 probability, and so you are trying to find those configurations that are allowed, those sequences that are allowed, and to find, in general, in coding, you're trying to find the most probable one. You're trying to do maximum likelihood, and you can do that with this algorithm.
Okay, sir.
Okay, perfect. So these are the two types of messages, and why is this natural algorithm? So these are, again, the factor to node and node to factor message. Why is this an algorithm that you should... yes, and one thing I want to add is that once you have all these messages, let's say at convergence, the BP approximation to the marginals of the marginals is given by mi at convergence, so when t is infinite, which is an approximation of the true marginals, which can be exact or not, is the product of all factors. Now I'm not removing any, I'm really making the product over all of them, of ma to I xi, which I then normalize. Integral of this numerator. Okay. So I'm considering, if you want, all the messages now that go toward the node from all the factors, and this is my approximation of the marginals, which can be potentially exact, if the, and then it can also not be exact. It depends. Okay. So in particular, I want to give you one case where this calculation is exact, in the sense that this you are guaranteed that this is really the integral over all x's except xi, I will denote it like this, of the joint law, which is indeed P of xi, the marginal. There is one case where you can prove that this is really an equality. And this case is when the factor graph is a tree. Okay? So theorem BP is computing the exact marginals if the factor graph is a tree. So there are no loops. Okay? So for example, this is a tree. There are no loops. Okay, so if you start from any node or graph and you want to go to another one, there is only one path. Okay. So you can show it by induction. I won't do it, but what maybe what I recommend that you try is just to prove it by just running a small example. So let me give you an example, and then I will give you the solution and just ask you to verify it. So let's say that you have the following factor graph. Psi1, x1, psi1, 2, 3, x2, x3, psi 3, 4, x4, psi 4, psi 4, 5, x5, psi 5. So this is a tree. Okay, it almost looks like a chain, but you have this slight differences. So this is a nice tree. So, and let's assume that our vector x, which is x1 till x5, takes values in -1, 1 to the 5. Okay. So let's assume you are interested in computing the marginal of x1, or another problem you can solve with belief ovation, which is actually the exact same problem as the marginalization, is to compute the partition function, the normalization of the factor graph itself. So let's say you want to compute z. Yes. So how do you compute partition functions from these equations? You just this is the same problem as the marginalization. You just call these messages z's, and you do not normalize. And if you are doing so, you are computing at the end. You can reconstruct the full partition function by just making the product of all these quantities at convergence for all x's. So, of course, computing the normalization of quality distributions or marginalizing, which is integrating all variables but one. Instead, computing the normalization is computing the integration with respect to all variables, are, of course, the same problem. Okay. So let's say that you are interested in computing the partition function. So z is sum over x. So I will do the example to the 5. Okay, so we have 2 to the 5 possibilities to sum over. And what's the normalization of the distribution? It's the distribution is just the product of the factors. I will not denote all the arguments because it's clear from the notation. Psi 1, 2, 3, psi 3, 4, psi 4, psi 4, 5, psi 5. Okay? And look, I can do something smarter than trying to compute this directly. This sum requires a number of operations, which is 2 to the 5, which grows exponentially with the number of variables. The number of variables is at the exponent there. What I can simply do is exploit this tree structure, this way the variables depend on each other, to simplify this computation. How? By just realizing that I can rewrite this sum like this. Sum over x1, which now just takes 2 values, minus 1, 1. So there are only 2 numbers of psi 1. I isolate the part that depends only on x1. Then I push on the right everything that depends on x2 and the rest. So x2 and x3. Okay, psi 1, 2, 3. Then x4. Psi 3, 4, psi 4, and then I push there psi 4, 5, psi 5. Right? This is the same object, of course. I've just pushed the sums in a smarter way. Okay? I've distributed the sums. Okay? And now let's count how many operations does this computation requires, which is the same computation. So here we have 2 operations to do. We have 2 there. Here we have 2 to the power 2, which is 4. And here we have 2 as well. So in total we have 2 plus 2, 4, plus 4, 8, 10. 10 operations. So you see, we went from 2 to the 5, which is 32, to 10. We have reduced the complexity. So it doesn't look like a big gain going from 32 to 10. But I claim that here, the computational complexity of this algorithm, if the graph would be much bigger, would scale linearly with the number of variables. Linearly with the number of variables times, so n times the maximum degree, because you see here, if there is a sum that I cannot divide in 2, this is still exponential, the number of operations is still exponential in the degree, in the number of variables in this sum. So let's say the maximum degree of these factors is 2, 3, 4, something small that does not depend on n. The computational complexity of exploiting this tree structure would now require a number of operations, which is the number of variables times the maximum degree, essentially. So this is linear in n. Instead, here, this is exponential in n. So you see, by just distributing the sum, you go from exponential to linear, if there is a structure that allows you this distribution. And such a distribution is exact, you can do that if the graph is a tree. And belief propagation is exactly doing this on graphs that are more complicated than this, than something that just looks like a chain. And indeed, what I ask you to do is to realize that these computations, this first sum and the second one, etc., can be computed, are exactly computed from these equations. If you write down the belief propagation equations for this graph that I wrote there, you will realize if you unfold the equations, really write all the equations, you will realize that what you're computing is this. You are distributing the sum. Okay? So that's why it's exact on a tree, and that's why it's also efficient. The computational complexity is linear.
Can you discuss this example with another type of graph, something in a mesh topology or any other topology?
What topology, sorry?
Can you discuss same problem with any other topology? Like you have discussed this particular graph with the tree topology, where you have taken all the nodes in a linear fashion.
Yeah, but the same example would work if you want. Here, if I start to branch another tree of any sort,
yes.
It works exactly the same way. I could add also here factors which themselves branch. I mean, I can do something much more complicated. As long as it is a tree, it will work the same way.
The same BP equation will work on that particular graph also.
Yeah, of course. If the graph is a tree, belief propagation is exact, and it's exploiting the same kind of mechanism. It distributes the sum in the smartest possible way. It's exactly the same. I just don't want to write it because it becomes, of course, complicated. So that's why I took a simple example, but it's exactly the same. It works on any tree. It's exact on any tree.
Okay, sir.
Because what it does, it's really distributing this sum is distributing it. Okay. So you should try. You should convince yourself of this fact. Okay. So, okay, I'm a bit long, so let me try to just say a few words about the approximate message passing. So we have this exact algorithm on a tree, but the subject of this course was the Spike-Wigner model. The Spike-Wigner model. And what's the distribution of the Spike-Wigner model, the posterior distribution? It was 1 over z, the posterior, times the prior, times the likelihood. Okay? So I can think of this as a factor graph, where this would be my factors psi, excuse me, there's a bug, psi i's of xi, so the prior plays the role of single factors, and this would be pairwise factors, psi ij. That depends on xi and xj. So the Spike-Wigner model, like any distribution which has some factorized structure, is a factor graph. But let's draw this factor graph. So let's say we have 4 variables. x1 is x4. I have one factor per variable, which is the prior, psi1, psi2, psi4. And then for every pair, I have a factor psi ij. So I have one factor there. This will be the psi 2, 4, one there, one there, one there, one there, one there. So this factor graph is anything but a tree. It's precisely the complete opposite of a tree. It's a fully connected graph. It's a fully connected graph. So why would I be spending an hour talking about an algorithm which is guaranteed to work on trees and try to connect that to an inference problem defined by a factor graph, which is the complete opposite of a tree? The reason is that belief propagation does work on this type of graphs as well. Okay, so the fundamental reason why belief propagation. So first of all, belief propagation is guaranteed to work on tree, but you can also run it on graphs which are not trees. So like usually BP was used to solve inference problems on locally tree-like graphs. So graphs which are sparse. It means that the average degree of nodes and factors is not dependent on the size. So if you increase the graph, you multiply the size of the graph by 2, the average number of neighbors of every node and factors remain the same. This is called a sparse graph. And in this case, there is a property which is the fact that every local neighborhood of any node or factor is a tree. So if you take a big enough graph with an average degree which remains bounded, which does not depend on the size of the graph, then in the limit where the graph becomes very large, every local neighborhood, so if you zoom anywhere in the graph and you don't look at the rest, it will look like a tree. Okay, and therefore you may hope that despite that there are very long loops in the graph, because of this locally tree-like property, the algorithm may work. And indeed, if these loops are not too many, belief propagation works and perform exact inference. Okay, but at some point, if the average degree becomes too large or there are too many loops, the algorithm may start to fail. And this is why you start to have a computational gap, a hard phase. At some point, there are too many loops and the tree approximation becomes too wrong. The algorithm does not perform well, and you have this mismatch with the optimal performance that you would get if you could solve the marginalization problem exactly. Okay, but you can hope that BP works also if there are loops. The issue is that here there are only loops. Okay, it's not locally tree-like. It's not sparse. It's the complete opposite. It's totally connected, this graph. But nevertheless, BP works. And the fundamental reason is that like in tree-like graphs, these fully connected graphs are such that if you look at the dependency, let's say the amount of dependency, so this is informal what I'm saying, between any two variables, even if they are directly connected by an edge. So in such a graph, there is no neighbors. Everyone is neighbor of everyone. There is no distance. Okay, it's not that some nodes are further from some others. They are all directly connected. So every neighbor, every pair of nodes, the point is that they are weakly dependent on each other. Like in tree-like graphs, it simply comes from the fact that most nodes are very far away from all the others. So the information that propagates from one to the other is passing through many other nodes, and somehow this dilute the amount of dependency between variables that are far away. Here, variables are that all neighbors, but the point is that look at a given variable, let's say this one. It is true that it is connected to all the others, but the point is that each of this interaction, for the model to be well defined, or at least for the model to be solvable by this kind of algorithms and techniques, should be weak. You see, and here it manifests itself by the following fact in the Wigner-Spike model. One of these interactions, psi ij, which is represented by one of these factors, is a function. It's a Gaussian distribution of xij. I mean, it's a Gaussian where xij appear like this in the mean. But you see that we have this 1 over square root n there. Okay, so this is a very weakly dependent function of xij. Okay, this mean is tamed down by this by this scaling, this 1 over square root 10. So you see that if you do a Taylor expansion of this, for example, at first order, it does not depend on xij. You need to go in higher order to see the dependency. So you have a really weak dependency enforced by these factors between any two variables. So it's a bit like a tree-like graph. It's as if these nodes were very far apart. Okay, and therefore belief propagation does work, surprisingly. At least in some regions, it does work if you are away from this algorithmically hard region, which is the region where the effect of these loops become too important. Okay, at some point this breaks down, but somehow there is a region where, due to the fact that every interaction here is weak, which is as if the nodes were very far apart, so the graph behaves a bit like a tree, then BP works. Okay, so the IMP, okay, so it's 9, so maybe we can stop there. I will use half an hour of the next lecture to tell you how to go from this belief propagation equation. I mean, I will just give main steps, main conceptual steps to go from this belief propagation to the IMP algorithm, and then we'll stop there, and then I will present the applications part of not just AMP, of statistical connections between statistical physics and inference and learning. Okay.
Okay, sir. Thank you so much. And we'll start the next session after 1 hour. That is at 1:30, sir.
Yes.
Exactly. What time will start?
Yeah. We do the normal schedule, so it's 1:30 for you. It's in 1 hour.
Okay, sir. We'll start the next session at 1:30. So thank
Okay.
you for the informative session. This session was really very good. I understand a lot of things. How
Okay.
a linear fashion, how exponential can be converted to the linear, how BP equation can be implemented in trees and other type of graphs. So it was very informative session, and all the participants are requested to join the next session after 1 hour.
Okay.
Okay.
Thanks.
Thank you,
See you
sir.
later. Goodbye.
Okay. Thank you, sir. Goodbye.
Thank you.
Yes, welcome back, Professor John.
Hello. Okay. Should I wait a bit? I see only you, me, and
You can wait for 2 to 3 minutes, let others join, then we'll start. So you can start your lecture. It's now 12 participants. You can start, sir.
I mean there's 8 participants because counting me twice, the webmaster and you. I mean, is it
Sir, I
normal that?
messaged in the WhatsApp group regarding joining of the link. Maybe within a minute or two they will join.
Yeah, but I mean, does it make sense that I just speak for? Okay, be I don't know. I can start.
Hello,
Okay.
good afternoon, sir. May I have a question? May I ask a
Yes.
question? Sorry.
Yes. Of course.
Yeah, yeah. Am I audible?
You are.
Okay, sir. Actually, I have a question. Like in the last lecture, what you told about the this thing of mm, for the variables and for the factor and the variables, like for uh, how much, like how many possible values of x, uh, like the related to that, the possible values of x, there could be many more, but what is the highest number of possibility that can be achieved by optimizing all the other variables connected to that function, or we call the factor, using the all incoming input messages from all our neighboring variables, like
Mm-hmm.
can it be explained?
I'm not sure I understand what you mean by what's the maximum number of possibilities. Possibilities of what?
So, sir, like for the each value of x, there could be a various numbers of possible values for x. So
Yeah.
what could be the highest number of achievable possibility for optimizing all the other variables that is connected to that one factor
Yeah.
and using the yeah.
Yes. Yes. So, I mean, you're asking. So, essentially, if the variables are, let's say, discrete. So, let's take a sum there. Then the number of terms that you need to sum, right, is. So let's say that every variable can take only two values, to simplify. Then the number of terms you would have to sum over here is 2 to the power, the cardinal of xa. So number of neighbors of the factor psi a minus 1, because you're summing over, you see all these xj's that are connected to the factor a, except 1. You're not summing over xi. Okay, so if instead these are integrals, if you are working in the real case, this would be an integration over r to the cardinal of this neighborhood minus 1. So this notation means the number of nodes connected to factor psi a, or the number of arguments of psi a. Is it your question? So the complexity of this integral or this sum, if it's discrete, is exponential, but only in the degree of the factor. Is it? I don't know if this is what you're asking.
I got a little bit, sir, but can you please explain this term for the neighborhood minus 1?
Why is it the case?
Yeah, the nodes connected. No, yeah, exactly. This are a real of this node.
Because this factor is connected to a number of neighbors of nodes, and I want to marginalize with respect to the neighborhood of this factor, and so I should integrate with respect to all variables but one. So I'm not considering this one, and I need to integrate with respect to all the neighbors. How many neighbors there are? There is that number, and I need to remove one corresponding to this one, and so I integrate over all these configurations of the neighborhood.
Okay, sir. So this process will go in a loop, right? For each and every term of
Yes.
a tree structure, we have to ignore the other for the one set of values.
Yeah, each time you compute a message like this, you need to remove one node. Indeed, this is a marginalization operation.
Okay, thank you, sir.
Yes. These equations are defined for every I and A, for every node and factor. So you have a set of messages of these two types, and for every node and factor. So basically you have messages like this flowing on every edges of the graph. Between every factor and node, you have a message flowing in that direction and that direction. So the total number of messages like this that you need to update is twice the number of edges that we could I could call like this of the factor graph. Okay, and you iterate these equations. Sorry, here I missed time. You iterate this equation. It's an iterative algorithm, and until convergence. Okay. Perfect. So in the notes there are references for belief propagation and all that. You can take a look. Perfect. So Okay, let me just say a few words about what's the problem with this algorithm when you want to deal with these kind of structures, which are fully connected graphs, and how to solve these issues. So there are multiple problems. So one of them is that there are too many messages. So like I said, the number of messages of probability distributions in the Billy propagation equations that you need to iterate in this algorithm is proportional to the number of edges like this between factor and nodes. Okay, so if the graph like this is dense, meaning that essentially nodes and degrees have, or in this case only nodes have a large degree, so the number of neighbors of this node in this case is n minus 1. So the number of messages is of the order of n squared, because every node is receiving messages from n variables, n minus 1, which is essentially n, and is sending messages towards n factors, okay? And this for every node. So the total number of messages you have to update is n squared. So it doesn't look much. I mean, it's still polynomial in n, it's not exponential, but for large values of n, this becomes quickly an issue, okay? While if the graph is sparse, meaning that the average degree of nodes and factors is not dependent on n, the number of messages you have to deal with is order n. Sparse graphs. Well, this is for dense. So this quickly become a bottleneck, okay? It's not practical. Another issue is that these equations are easy to implement if these integrals are actually sums. So if you're working with continuous variables, these would be sums. I will rewrite them in terms of sums. Oops. Okay. These are all the xj's belonging to the neighborhood of A except xi. So performing these sums is possible, okay? So again, this is okay, because doing sums like this numerically is fine. While if you have to compute integrations, even if the number of variables that you have to integrate over is 3, 4, it becomes quickly a big issue. Okay, you don't want to have to compute integrals for all of these messages. So it's not an algorithm which is very well suited for continuous variables. Written like this, it's well suited for discrete variables. Okay. Another issue is still related with this fact that you may want to apply this to inference problem where the variables are continuous. That on top of requiring to compute integrals here instead of sums, how do you encode? How do you represent these probability distributions? Because you see, if xi is a real variable, it can take let's say any value between 0 and 1, let's say, or between 0 and 2, whatever. You have to. This is a function. It's a probability density. Okay, so how to encode efficiently in the computer a probability density if it's not parameterized in a nice way, like a Gaussian or like some known form? You cannot. The only thing you can maybe keep in memory would be an histogram of this probability distribution, which is very demanding in terms of memory. Okay, so it's hard to keep in memory generic probability distributions which do not have some specific parametric form. Okay. So all these issues make a priori this algorithm not a good candidate to perform inference with continuous random variables on dense graphs. Okay. Also because you see if the graph is dense, here you would have an integral over r n minus 1, which is again which is as hard as the original problem. It's an integral over an exponential volume of n. You would have to marginalize with respect to all the variables but one, but given that every factor would be connected to all the others, you cannot. Okay, so you have to find some other way. So what I just said here is not an issue for the spike beginner model in the sense that every factor is connected to only two variables, okay? But if the factors were connected to many variables, in this case, you cannot do anything, okay? You can do something when variables have have a high degree, but factors still have a low degree, okay? Okay, actually, this is not true. You can also solve the issue if the factors have a high degree, but I won't talk about it. You can use, for example, this to solve regression problems and things like this. But let's focus on this spike model. So the question is, how do you simplify this algorithm? And I will not give the detail. I will just explain the idea. The thing you can realize is that if you look again at these equations, so let me write them for a generic continuous valued variable. So okay, no, so let's do it for the. Let's write the BP equation for the spike Wigner model. Wait for my notes. Yes. So if you write down these equations in this context, what you get is the following. So you just apply what I've just written and you use it for the spike model. And so what you get is m factor ij to variable I times t xi is proportional, so up to the normalization. I'm not tracking normalizations, to the integral with respect to xj of the distribution that j sends to factor ij times the factor, and the factor is exponential minus 1/2 yij minus square root lambda over n xi xj squared. This is our Gaussian. Okay, so this is the psi ij. And that depends on our observation yij. It's our factor. Okay. While the other messages, the node to factor, is the product of all factors. So there is the factor coming from the prior. This is psi I times the product over all k. So a node is receiving information from the factors from connected to all the other nodes. So it's a product over k different than I and j of mik to I at t xi. Okay. So this is BP for the model of interest. So the key point in order to simplify the algorithm is to realize that you see here again, because this exponent is very weakly dependent in xi/xj, I can do a Taylor expansion, right? So I can do a Taylor expansion of this part, Taylor expand in 1 over square root n, thinking that n is large, okay? 1 over, yeah. And if you do so, what you can do is compute the means ij. You can write the equations for the means and the variances of these messages instead. And the variance vi to ij. So I won't do the derivation, but the main point is that, you see, because this thing is small, if you do a Taylor expansion of this exponential at second order, what you realize, so you will linearize this exponential, and then you have a quadratic term in the axis. You will so the linear term, you see, it will be just an integration of m against a term linear in xj. So it will be a function of this expectation, okay? And the second order term in the Taylor expansion of this exponential will make appear xj to the square. So you will have when you integrate with respect to m, if you give a name to the integral against such a message of x squared, and you call it v, it's like the variance of these messages, you will have these variances that will appear. And what you can show is that all the smaller order contributions, the higher order terms in 1 over square root n, they are negligible. You can forget them. So what does it mean? It means that somehow, by exploiting this Taylor expansion there, the fact that these interactions between nodes are very weak, I can close the equations, so I can simplify the equations, and instead of working with these generic probability distributions, I can just work with their expectation, their mean, and their variances. And all the higher order moments do not matter. So what does it mean concretely? I'm just reparametrizing these messages in terms of Gaussians. Okay, this is the kind of central limit type of argument. So it's just the formal, like this Taylor expansion is just the formal way to show, by being able to show that any higher order terms greater than first and second moment can be neglected. You are showing that you can only parameterize. Basically, these messages are Gaussians. They're almost Gaussians, and you can discard the correction to their Gaussian behavior, because parameterizing them by Gaussian is asymptotically exact. They behave like Gaussians. And now that they have, if they're Gaussian, everything becomes fine, because it's easy to keep in memory a Gaussian distribution. You just need to keep the first and second moment in memory. So basically, you are reparametrizing these generic functions, which are probability densities over continuous variables, in terms of just their first and second moments. Okay, and then doing so, you can actually close the equations. You can rewrite entirely the belief propagation equations just in terms of their first and second moments. So you will obtain iterative equations on these b's and v's. The m will completely disappear. You will obtain an iterative equations that update the expectations and variances of these belief propagation messages.
So that
So
it means instead of transmitting the M, we can transmit the message mean and variance.
yeah,
We will
exactly.
convert the whole message sequence in either by taking the mean of that equation or by taking the variance. That is the
Yeah,
first
exactly.
and second order derivatives. Okay, sir.
That's the first step. Yeah, it's a Gaussian parametrization of these messages. But this is the point I'm trying to make is that this is not just this Gaussian parametrization is exact. It's not. I mean, it's asymptotically exact. When n is large, you can show that these messages are truly Gaussian. So there is no approximation when n is sufficiently large. It's an exact relaxation. Okay, and you can just show that by doing a Taylor expansion of these kind of terms, which are very
In
weakly
every case,
dependent.
it is possible to convert it, or in some different cases we can convert it into this Taylor expansion into the first order or second order equation.
Different cases of what? What do you mean?
Like you have taken the case where the value of n is too large,
When n is large, yes.
then only we can convert it into the mean and variance.
Yeah. So this Gaussian relaxation only makes sense for very large instances of the problem. But actually, in practice, if you so let's say you do these derivations, you obtain the final algorithm written in terms of these means and variances. So which is really a Gaussian relaxation of these messages, and you run that instead of the exact equations on an instance of your problem, which is of size, I don't know, even 500, which is not so large actually, you will see that there is almost no difference. So when I say very large, it doesn't actually need to be so large to work out this type of approximation. But what you can prove mathematically is that these relaxations are exact when n goes to infinity. Only the first and second moment matter when n is very, very large. Okay? So you can do that, and at the end you obtain another algorithm, which is just iterating these two objects, means and variances. So I will not write it. So in my notes, not the one I've shared, but at the beginning I say that there is a longer version of the notes that I've shared with you. If you click on these longer notes and you are interested to understand the details, I explain in very much details these derivations there. Okay. So that's the first step. It's going from generic probability distributions here to Gaussian distributions. So it's parameterizing this by first and second moment. So then you close the equations on this first and second moments. And the second issue that you want to solve, you want to simplify, is that still you see these moments. So you have a B and a V for every messages like this, but you have also a B hat and a V hat for every messages like this. Okay. There are still many, in the sense that now we're just dealing with numbers, which are these numbers instead of probability distributions. We're just tracking the moments of these distributions, but there are still many such numbers because you see they are indexed by edges. This number is indexed by an edge that go from I to factor ij, and vice versa from ij to I for the other type of message. So there are still order n squared quantities to update, and therefore equations to update in time at every iteration. This is too much. For practical problems.
This gives the high complexity in the network. Again,
yeah, it's still exactly. So it's still high. Like from the perspective of computer science, it is not, because everything that is not exponential in n is said efficient. But for practical purposes, this is too much. What you would like is an algorithm which complexity scales as n, is linear in the number of variables. So the next step, which again I won't explain, but is again based on a Taylor expansion, but this time you can show that basically the fact that these quantities are computed without considering one of the factors, so you see this represents the expectation of this probability distribution where all factors are connected to node I except one. You have removed one. Okay. This is the variance here. Okay. And what you can show is that you can rewrite this quantity in terms of really the marginal means. So really, you are closing instead the equations in terms of quantities, which are the integral of mi and same for the variance. Okay. With and without a hat. So you see, it's like if in the belief propagation equations, I'm kind of forgetting that I should consider one node or one factor out in these equations. I'm trying to close the equations on really these quantities, which are the approximations of the marginals themselves. But of course, this is not correct. So, but what you can show is that nevertheless you can close the equations on these quantities, but up to a correction. So you again do a Taylor expansion if you want in. You are kind of correcting for not considering the removal of a node or a factor here, and you pay a price to that, which is a first order correction, and you can compute it. So overall, at the end, you are closing equations only on quantities like this, which are indexed only by the nodes. And of course, they are related to these quantities by some corrections due to the Taylor expansions that you're doing. So maybe this looks a bit...
Is it always necessary to convert a generalized model into a Gaussian model only? Why not any other parameters to follow?
I mean, you could say, okay, no, I mean, you could parameterize this distribution in other ways, but the thing is that the Gaussian parametrization is exact, because if you do really the Taylor expansion of this, you realize that only first and second moments matter, and a distribution that is only parameterized by first and second moment is a Gaussian. So if the other moments are functions of the first and second moment, they are Gaussians. And basically here this is the case. If by Taylor expansion, if you work out the things correctly, you would realize that higher moments are only function of the first and second moment. So they are Gaussians. So there is no smarter or alternative choice to do in this case.
Okay. Majorly the exponential factor also can be easily converted in a Gaussian distribution.
Yeah, if you want, it's already natural. You have already this exponential form there. But actually, here this could be something else than a Gaussian if the interaction, if this factor would weakly depend on the variables, in the sense that you would have a factor like this in front which goes to 0 when n is large. Even if this would not be a Gaussian, the resulting measure would still be a Gaussian by Taylor expansion. Okay? But, okay, so at the end, you obtain this. Sorry, I need to charge my computer. Give me just 1 second. At the end, you obtain an algorithm which can be written in terms of only in terms of matrix vector multiplications. And the meaning of the quantities that you're updating is precisely this, is the mean and variances of the marginals that you're trying to approximate. The marginals you're trying to compute, for the same reason that I explained here, they are also Gaussian. And you're trying to computing the mean and the variances. And you see these Gaussian marginals that appear are precisely related to the effective denoising problem that appears in the replica formula. You remember that in the replica formula we have that the formula tells you that somehow the high dimensional problem becomes asymptotically equivalent to denoising just scalar variables. And this, okay, induces Gaussian marginals. And so the relation can be understood in terms of these Taylor expansions that I'm mentioning at the level of the cavity equation. So it's a bit difficult to say much more here in few minutes, but this is how this problem appears somehow. The derivation I'm talking about shows at the end that somehow the belief propagation equations are trying iteratively for each variable to solve a kind of denoising problem like this. It's very much connected. Okay, so I know that it's not entirely clear, and this is fine, but I think the main point here just is that we have this algorithm, belief propagation, that can be simplified for dense graphical models and be used simply by reparametrizing these messages in terms of Gaussians. Okay, and so this is really the key point. This is the hidden also central limit theorem kind of argument that I mentioned at the beginning. Okay, okay. So last remark: this algorithm comes also with a bunch of rigorous analysis. There is something called the state evolution, which is a series of theorems that precisely describe the performance of these algorithms when n goes to infinity in the large size limit. And the surprise, maybe I can just mention this to close this part. The surprise is that these theorems at the end, so you remember this was the equation that the replica formula tells you. It tells you that this parameter q in this formula, which represents physically the overlap, the inner product between the base optimal estimator of the signal and the signal. Okay, this is the physical meaning of this q, because it is related to the error by this theorem. Okay, from this you can see that this q0, which is the minimizer of this replica formula, is precisely this angle I was mentioning. So the way to find this q is to solve this equation q that I wrote there. Okay, it's a kind of self-consistency equation. You have q on the left and you have q on the right. The theorems that describe this belief propagation, or that we call approximate message passing when we use it on dense graphs, but at the end it's the same algorithm. These theorems tells you that the inner product between the estimator obtained by, so at every time this algorithm will tell you what are the means of the messages, which are an approximation for, so at convergence, the means of these messages in this algorithm are an approximation for the posterior expectation of the components. This can be a good or a bad approximation. It depends on how the quality of the data and the signatures row, but this is the goal. What you hope is that these things are approximations of this posterior means. performance, the overlap between this vector of estimates and the ground truth is given by a theorem called state erosion, and it tells you that actually you can even track the performance of these things in time at every iteration. And what it tells you is that the overlap, so if you look at the inner product between these estimators and the ground truth, let me call it Q AMP for this algorithm at time t, then this Q AMP at times t, when n is large, is given by this following equation. X star plus z. Okay, so you see that it's the exact same equation and the replica formula, except that now you have time there, because you are tracking the performance of this iterative algorithm. This is the equation that describes when the problem becomes large, how the vector, your estimator obtained through this algorithm, is aligned with the ground truth x star. And it's given by the same equation. So what does it mean? It means that when the solution of this iterative equation converge to the solution of this equation, which minimize the replica formula, because you need to pick the minimizer to find the information theoretic value, the Bayes optimal value, then this algorithm is Bayes optimal. However, if this equation has multiple solutions and the solution of this equation describing the algorithm, which should be initialized at t equal to 0 with 0, because at the beginning your estimator is orthogonal to the truth. If this equation converges to another solution, then the algorithm is suboptimal. And this is what allows to draw this picture. This is the region where the equation describing the performance of this algorithm converges to another solution, which is not the one given by the replica formula. In this case, it would converge to Q equal to 0, or equivalently to the error equal to 1. In this region, this iterative equation describing the performance of the algorithm, initialized from 0, meaning from no information about the signal, will converge to the same solution as the Bayes optimal one. And so you can show that you have a Bayes optimal efficient algorithm, which is belief propagation. Okay? Perfect. So this closes this discussion. We have a complete picture now of this phase diagram. We have understood through the replica method how to obtain the Bayes optimal performance, through random metricity theory how to obtain the spectral PCA, and through a very shallow introduction to belief propagation, we have seen that there is a Bayesian algorithm that whose description matches what the replica formula tells you, at least in some regimes, and it gives this red curve here. Okay, so I know very well that this last lecture was very dense and fast, and I'm sorry about this. It's I wanted to spend more time on this, but now I would like to show you more applications. So if there are questions, I can answer. Otherwise, I refer to you to the detailed notes, not the ones that are that I've shared at the beginning, but if you look at the very beginning, I say at the first page that I give a link to a more extended set of notes that I've written, and you can take a look there. All the details are present. Okay, so if there are no questions, maybe I can move to the more, let's say...
Yes, any questions from the audience side?
Okay.
Do you want to ask something?
Yes, ma'am. I have a question.
Okay.
Go ahead.
Yeah, one thing what I have noticed and compared is that this this method of the whole method what you have told in today's lecture and previous lectures is having the resemblance with the S matrix theory what we study in physics. Like
Which
so
theory? Say it again. The
S matrix theory.
S matrix theory. I've never heard about this. Okay, what is it?
Yeah. So actually, S matrix theory is basically about the quantum mechanical applications for the phase transitions and the particle interactions, and its comparison is done with this spike Winger model for the low rank signal
Mm-hmm.
and particle interactions for the S matrix theory. So most of the things and algorithms, the mechanism are similar between these two uh, things, like these two processes for the spike Winger model and the S matrix theory. So both of the processes tell us about the asymptotic limits and universality. Okay,
Uh-huh.
so one thing what I want to infer from this and want to ask, like if someone have to do the discrete and continuous simulation for a data set, so what like uh, like for example, if I have to do a real time measurement for a data or a signal or whatever messages it is so like how to interpret the things if we have the different models with us, but we don't know the right efficiency and the output, like how can we get the exact and less error output for from this say from the same kind of models, like how to differentiate between those things. Like one physicist, like for example, if a physicist have to interpret the data for the real time measurement of any movement of, like for example, electrons or any particle or any data system, so how can we get to the conclusion that this model or that model is giving us the more efficient or the more accurate or less error outputs? Like how to get to that decision?
And I think if I knew the answer, I would be probably with a lot of big prices. It's a very hard question. So your question is, for a given physical process, how can we make sure that we select the best model among a pool of candidates? Is that correct?
Yeah, right.
Yeah, I mean, I don't know in general. I mean, you can always assume different. I mean, let's say in machine learning there is an answer. So if you, and I'm not entirely sure this is precisely your question, but if I interpret your question as, imagine that you have some data coming from some experiments that could be physics experiments or whatever, and you have a pool of candidates models to process this data and make inferences, how to select the best model, right?
Yeah,
Uh,
right. Yeah,
yes, so there is no easy answer, but at least in machine learning there is a recipe. So in machine learning, usually, so the goal is to train a model from data to predict the output associated with an input, for example. So is to find a relation between input and outputs given examples, given data, which are of the form input and output. So this is a very generic setting. It's called supervised learning. And in this case, you may have many possible candidates models to train from the data and how to select the best one is done as follows. You should essentially train all the possible models that you have in mind. Of course, this has a computational cost, so you train as much as you can. And then you would select the one, you do what we call cross-validation. You would select the one that is able to predict the output associated with inputs that were not part of the training data. So you need to select the model that generalizes the best, that is able to fit the relation somehow on data not used for the training. This is called cross-validation, and it's a very generic approach to model selection. So I don't know if this answers your question.
Okay, yes, sir, I got it. Thank you.
Okay. Great. So let me now. Basically, this closes the course, and I would like just to spend the last 10 minutes maybe of this lecture and the last lecture to now show you let's say the broader context. Maybe I should have started with this to motivate you guys to stay focused for the course, but now I want to show a broader overview of the kind of inference learning communication problems where all these techniques that I've presented are of direct use. Okay, so just to show that I'm not lying to you, that what I've presented is really not specific to the Spike-Wigner model, but can be applied in a much broader context. Okay, so I can stop sharing here. Okay. So we have 10 minutes. I can start with this 10 minutes and then we continue after.
So you have to take the last lab session also on a hands-on training? Finish.
Yeah, but we decided with Jaspal that I'm going to do this lecture instead. I wanted to show, let's call this the hands-on part. It's the application part. Okay.
So by showing these applications, you will the course will be over now.
Yes. So I will spend 10 minutes now to start, and the next lecture will go in. I will show more applications. Okay.
Okay.
Perfect. So do you see my screen?
Yes, your screen is visible.
Okay, so the goal of my goal now is to show you that this key notion in the course, that is that of phase transition between different regimes in the problem, between different phases. So the phases we mentioned in the Spike-Wigner model are the statistically impossible phase, where reconstruction of the signal is impossible. The algorithmically hard phase, where it is possible but no efficient algorithm can do so, and the algorithmically easy phase, where efficient algorithms become optimal. These kind of phase transitions actually appear in tons of contexts, which are both in data science problem, in data processing, but also beyond. So the phase transitions are essentially very universal phenomena. I'm sure that many of you know that, but I will try to show you this. So again, by phase transition, do you see my pointer?
Yes, sir.
Okay. So by phase transition, I mean again an abrupt change in the behavior of a complex system as a function of some control parameter, and this abrupt change is manifests itself in the change of some order parameter, of some observable about the system that can radically change at some value of the control parameter. Okay. So okay, let me again connect. Let's start again from the basics, because my understanding is that most of you are not physicists. So I just want to make the connection with physics even more clear. So in physics, you deal with atoms, molecules. Okay, they are very small objects, and you have tons of them. Okay, so for example, in water, in any physical system you may be interested in studying, the typical number of entities that you're describing is the Avogadro number, which is of the order of 10 to the 25, which is really a large number, which is orders of magnitude bigger than the types of numbers of scales that appear in astrophysics.
Slides are not moving. You are at the first slide. Yes, now you are at the third slide.
Yeah, I will share the screen instead, like this. Okay. Okay, I was explaining that. Let's say in physics. Now, do you see?
Yes, we can see.
Okay. So in physics, the typical systems you're interested in are water, molecules, things like this. So they're very small objects, but you put tons of them together of the order of the Avogadro number, which are orders of magnitude bigger than the types of numbers appearing in astrophysics. This is much bigger, for example, than the number of stars in the galaxy or things like this. So these are really big numbers. And so this is a quote that I already used in the course by Philip Anderson, who got the Nobel Prize in physics. More is different, or equivalently, the whole is more than the sum of its part. So even if the molecules are the same at any temperature, and the physics that of interactions between them remain the same at any temperature, they change. They change a lot as a function of the temperature. At the global level, they behave as a solid if the temperature is small, then as a liquid, and then as a gas if you increase further the temperature. Okay, so this is what I mean by phase transition. Okay, citing Anderson, the behavior of large and complex aggregates of elementary particles is not to be understood in terms of simple extrapolations of a few particles. Instead, at each level of complexity, entirely new properties appears, and the understanding of the new behaviors require research, which I think is as fundamental in its nature as any other. So this is the starting point of this is the motto of statistical mechanics. Okay. So when physicists talk about phase diagram, it used to be only restricted to such physical systems like water. And for example, for water, the phase diagram looks like this. It tells you in which state is the water as a function of the pressure and the temperature. So here you have the liquid state in this region. Here it is an ice. So when the temperature is small and or the pressure is high. If you increase the temperature at any given pressure, at some point it will become liquid, and at some point it becomes a gas. Okay, so these are the phase transition lines between these different regions. In particular, the Earth lives there, and this is the variation of temperature. So we observe all the types of phases for water, because the temperature varies. Venus lives here on the phase diagram, so all the water you find on Venus is in the gas form. In Mars, all the water is in the ice form. You are there in the phase diagram. Okay, so this picture is makes the connection with physics. So this is a kind of one slide course on physics, but you see, this is what we call the free energy in physics. This is the related to the Shannon entropy in the context of information processing systems. But so it's the way physicists describe complex systems, and the replica formula was an example of such an object. It's like a free energy, elementary information. It tells you in which phase the system lives at a given value of a control parameter. So let's say for physical system, the order parameter would be the density of particles. So it would be, let's say by definition, 0 for liquid. it would be negative for gas, and it would be solid for positive values. Okay, so it's just a convention to set to 0 the density for liquid. And the free energy is a kind of function that tells you where the system lives, in a sense that you should select always the minimum of this free energy. Okay, so if the minimum is at the liquid state, you would observe in practice the liquid state. But at some point, if you decrease the temperature, you observe this red curve. The system, now the minimum is at the solid state. It means that the system, it is more favorable from the energetic and entropic point of view to be in the solid phase. Okay, and the moment where this function has two minima at 0 temperature here, basically this is the moment where the phase transition happens, when the equilibrium becomes the solid instead of the liquid. Okay, so these are repetitions of what I said at the beginning of the course. Okay, it's okay. 11. Maybe I can just finish these slides and then we continue the next lecture. In physics, we like to describe things in terms of control parameters, which are this quantity that an experimentalist can tune, like the temperature, the pressure. And the way we describe the system at the macroscopic level are these so-called order parameters. So let's say density of particles, the magnetization in a spin system, like the Ising model that we've studied, or any other macroscopic global property of the system. In the context of inference, it would be the minimum mean square error, the overlap, things like this, the overlap with the signal. So this is really the description of the model at the large scale, not the microscopic scale. And so there are two terms that contribute in constructing the free energy in the function that I was showing before. It's a competition between two terms. One is the energy, which is essentially the cost for the system to be in the macroscopic state O, described by these order parameters. And the lower the energy, the more order there is in the system usually. So in inference, the energy, you remember, is essentially the log likelihood. So if you write down a post-error distribution in Boltzmann form, in the exponent, we recognize what we call the Hamiltonian, which is the energy. And it was the minus the log likelihood. Okay. The entropy instead is the logarithmic number of configurations corresponding to a certain macroscopic state. It's the degeneracy corresponding to a certain value of the order parameters. So, for example, in inference, again, it's the number of, it would be, so the microscopic states in inference are all the possible values of our estimator for the unknown parameters, and the order parameter could be the minimum in square error, and basically the entropy would be the number, the logarithmic number, the volume of configurations of values of our vector that are in agreement with a certain error with respect to the signal. So there are many vectors such that their square deviation with the signal is roughly the same. If you are counting them, it gives many. There are exponentially many, and the log of this is the entropy. So the higher entropy, usually the more disordered is the system. Okay, and the free energy is the difference between energy and the entropy, and the entropy is multiplied by the temperature. This is essentially a definition of the temperature. Okay, so maybe we can stop there, and what I will show you next is that this vocabulary, these notions, are really universal and can describe financial markets, imitation effects, and of course information processing systems and computer science, as I will show you. Okay, so we meet again in an hour, I guess, right? Or no? When do we meet?
Sir, approximately after 1.5 hours, exactly at 4, we'll start the next session. or after 1 hour? What you want?
I see that the
It is
schedule
at
was supposed
3:30 to 4:30. Yes, after 1 hour in the
to be
written.
1 hour. Okay, we
Oh,
meet in 1 hour then.
okay, okay. So
Okay.
all of you
See
are
you.
again requested to join the link after 1 hour at 3:30. And thank you, sir. We'll meet you
See you
again
later.
after 1 hour.
See
Okay,
you in
sir.
an hour.
Okay, sir.
Good evening, everyone. Good evening, John sir. Good evening, Julio, doctor.
Hey, Jaspal. Yeah, sorry, I had the microphone. Hi, Julio. Hi, Jaspal. So, I'm sorry, I cannot wait. I have a meeting at the end of in 1 hour from me. So it
So
was
you
super.
can start. You can start. I will quickly put up a message in the group too. You may start, please. Huh?
Yeah. Okay.
Okay.
All right. Do you see my screen? I guess yes. Now, no.
Yes, sir. We can see there.
Okay. So let
Yes.
me. Okay. So let's finish this series of lectures with examples of why phase transitions are so useful to study. So this is really a course for people. Yeah, this is the goal is really to give you an overview of where the kind of methods we studied can be used. So let's consider a very simple model of imitation effects. So the following model is modeling how votes. It's a very simple model of how can people can make very important decisions and without thinking too much. So it's a model where basically every voter is a binary variable. So it's like a spin in physics, takes value plus or minus 1 corresponding to choice A or B. You have n voters. And so the way we're going to model these votes is the following. Every individual will be influenced by what we call a mean field. So it's and therefore the connection with mean field spin models, of course. You see that somehow the probability that at a given time, so it's sequential dynamics, the voter I votes for the candidate A at time t, which in this language is a probability that SIT equal 1, will be proportional to exponential of the trend divided by a temperature. Okay, so what is the trend? The trend is just the average vote at time t. So basically what a voter does at any time is that it's sampling what people are doing, computing the average of what they're doing at that time, and this average will bias the vote towards 1 if this trend is positive, so more people vote for 1. If instead this trend is negative, more people vote for -1, then this probability will be less than 1/2, and the person will tend to vote for choice B. Okay, so very, very simple model, and you see, of course, that this trend is exactly like the magnetization in the Ising model. So perfect. So what is the temperature in this simple model? It plays the role of a kind of level of independence of individuals with respect to the dominating trend. You see that if the temperature is very high, this probability becomes essentially, this exponent becomes essentially 0. So the probability to vote 1 will be 1/2. It will be uniform choice for every voters. So it's a completely disordered voting process. Instead, if the temperature is low, then this exponent becomes very important, and every voter will tend to vote with very high probability the same as the average. Okay, so it will be strongly influenced by the others. And so if you simulate the system, it's very easy to implement in Python. So I did it, and you see what's the average vote. So you're computing this kind of average vote, the trend actually, which is like the magnetization, as a function of time when the system size is 10. Okay, and what you see for a given temperature is that you have large fluctuations. The system stays close to +1 or -1 for a short amount of time. Then you have this this abrupt changes like this, but it's very erratic. This is for small size. But now if you take the very same rule and you take n equal 100, so a bit bigger, you see something very different. You see a polarization effect. So you start from an average of 0, around half of the people vote for +1 and the other for -1. And then you have a polarization of all the people vote, like in this case, 80% of the people voting for the same candidate, -1, candidate B. And you don't see anymore the system escaping this state here. So you will stay there for a very long time, okay? And if you increase the size even more, you will stay there forever, essentially. So it's a very strong polarization effect of the voters. And this is what we call a spontaneous symmetry breaking of this system, in the sense that here you have a symmetry between the +1 and -1 state, and you fluctuate from one to the other. And here you stick to one of the states, to everyone voting for the same candidate, and you will never escape this, even if the system is symmetric between the two, right? Between the two candidates, you could have randomly gone to the other candidates so that the average was closer to 1 instead of -1, and you would still stuck there forever. So it's the random fluctuation at the beginning of the dynamics that decide which state is chosen, but then you don't move from there anymore. So really more is different. You see a very qualitative difference between small and large system. And you can think of this as a very simple model of imitation in finance also. Instead of voters, you have buyers and sellers, and this kind of simple models, and of course much less simple models, are used to understand what are cracks, financial cracks in finance. So this is, for example, the value of the Dow Jones in the 80s. At some point, you've seen a big jump in the overall financial market, and this is a kind of phase transitions which is of the same nature as the simple model we just seen. Okay, so let me connect this to what we've studied in the course. This is the very same phenomenology as the ferromagnetic model, right? So you remember we studied this model of binary spins, which are these variables that are interacting with all the others. So this is our factor graph, where every edge is an interaction with the others. And every of these nodes carry a binary variable, ±1. And you see that at high temperature, if you simulate this system, indeed, you see that the magnetization, which is the average direction of these arrows, fluctuates around 0. Okay, so this is the paramagnetic state that we defined. And instead, if you lower down the temperature, you see again a polarization. So you see that all the arrows will point in the same direction, and you will stick there. So this is the ferromagnetic state. Okay, so it's the exact same phenomenology as for these voters. Okay, and again, you can describe this in terms of free energy. So you see that, which again quantifies the competition between energy, therefore ordered configurations, and entropy, which favors more disordered interactions, which are more numerous. If you look at the free energy of this model as a function of the magnetization, which is, you see that for high temperature, it has a single minimum in 0. So this is this region at high temperature, it's the paramagnetic region. And if you lower down the temperature, the free energy becomes very flat there. And at some point below the so-called critical temperature, Tc, the free energy has two minima corresponding to the +1 state and -1 state. So this is the moment where the system pulls.
Your mic's off.
So for how long have I been talking without the mic? For a while, no?
No, 15 seconds.
15 seconds. That's weird.
10
okay,
seconds.
it's very strange. Okay, so if it happens again, please tell me. Thanks a lot.
Okay,
Perfect.
sir.
So thanks a lot. So so no, I was just saying that in the voters model, these arrows, the spins in the Ising model, of course, are the voters, and they fill the average trend. They try to do the same as all the other arrows. So this is the link with ferromagnetism. So let's see also the kind of phenomena appearing in animal behaviors. I really like this example. So if you go to Rome in Italy in the summer, you tend to observe these big flocks of birds, and they seem to follow very interesting and rather coherent dynamics. They follow each other's like this. And this has been studied a lot by statistical physicists in Rome, in particular, and they identified also emergence of ordered trend phases, like in the ferromagnetic Ising model, where you go from paramagnetic to ferromagnetic. In this case, it's a bit richer. So this is a subfield of what we call active matter, in the sense that now every individual particle can take kind of informed decisions based on observing its neighbors. So these insects are kind of observing locally what is going on, and they're adapting their behavior according to their neighborhood. And you see in these systems very rich phase transitions and various phases. You have, for example, the swarming states, which are disordered states where basically every insect or birds fly away, fly randomly around a kind of center of mass. Then you have the polarized state, which is the equivalent of the ferromagnetic phase of the Ising model, where they kind of follow same common direction, and this is an ordered phase. And then you have the Milling state, where they also move coherently, but kind of turn around center of mass. They kind of move as a circle like this. So there is no global movement. The center of mass is fixed here, while in the polarized state, the center of mass is moving. Okay, and this can also be described through the language of Ising type of models. Okay. These are very nice pictures. So this is the Milling state in schools of fish, and these are kind of states which are polarized in birds. Okay. Let me also mention an interesting thing that people understood. Biological systems like birds and things like this, they tend to live very close, to place themselves naturally as a complex system as a whole, very close to phase transitions, in the sense that these kind of states are something in between disordered and ordered state. And the reason is that when a complex system lives close to a phase transition, the information like information propagation between one part of the system, one particle or one bird, to another one which is far away from it, is much more efficient. It happens much faster. So this is related to what we call criticality. So information processing becomes very, let's say, efficient and fast in critical systems living close to phase transitions, simply because close to phase transitions, somehow you can show that you have very long range dependencies and interactions between particles, when calling particles generic entities in a complex system. You have very long range dependencies between particles which are even very far apart. Okay, and it implies a fast spreading of information. So okay, so let me move directly to computer science. So let's see some problems. Let's move away from physics to computer science and combinatorial optimization. Then we'll go towards communications and inference later, and then machine learning. So, but let me start with classical problems in computer science and see how why the analysis of phase transitions and statistical physics is useful in this context. So the main, let's say, question one is interested in answering in a whole field, so overall in computer science, is the following one. Why are some problems easy to solve and some other problems are hard to solve? What makes a problem hard? And is there some generic features about problem that can we know in advance whether a problem is hard to solve? And by hard, I mean with an algorithm or not. In general, the answer is no. It's not clear in advance whether a problem is hard, but you can approach these questions through statistical mechanics methods. So let me start with the grandpa, the father of all the problems in combinatorial optimization, in particular the birth. It's the analysis of this problem gave rise to what we call graph theory now, which is the problem called the 7 bridges from Königsberg. So Königsberg is a city here just above Poland, which is nowadays called Kaliningrad. The name has changed, but at that time when graph theory was developed, it was named differently. And so in this city there are three banks and an island in the middle, and you have bridges in between. Okay, and what people were trying to solve at that time, because it was a kind of game, is can you find a path that crosses all bridge a single time? So can you draw a line here that passes through all the bridge a single time? And so you have many possibilities to try. There are many places to start from and many choices to go everywhere. So you have a combinatorial number of possibilities. It's very many. So what you can try to answer the question is just try different ways. So people were trying for days and days to answer. But there was no systematic solution. We could not formally answer that question. So the only way was just trial and error. Okay, but Leonhard Euler, who's a Swiss mathematician, came out with a solution, and to do so, he developed graph theory. Do you still hear me? There is no problem? I hope so. Okay, now I have a doubt. Do you hear me?
Yes.
Yes, okay, perfect, thanks. Yes, okay, perfect. So the solution that Euler found came through abstracting a bit the problem. So what he has done is the following. He took the map and he associated every bank and the island to a node. So every piece of land which was disconnected from the others by due to the presence of water in between was associated with a node, a dot. And if two banks were connected by a bridge, then he was putting a bridge between these two nodes that he called an edge. Okay, and so he drew the first ever graph. Okay, which is an abstraction of this problem. And Euler found that he could prove that if more than two nodes have an odd number of edges, then there's no solution to the 7 bridge problem. So he provided an efficient algorithm to answer this game. You just had to count the degree of every node and to see if whether more than 2 had an odd number of edges. In this case, you knew that there was no way to pass through all the edges a single time. Okay. So this is an instance of an easy problem. You have a problem. Can we find a path crosses all bridges a single time? So this is called in computer science the problem of Eulerian path for obvious reason. And the algorithm is simple. Just check the number of edges of the nodes, and you compare with what Euler said. If the answer is no, there is an Eulerian path, and if it's yes, there is not an Eulerian path. And of course, checking this is just counting the degree of every node. It's an efficient algorithm in the sense that the number of operations you have to carry just grows with the number of nodes, or actually with the number of edges. Okay, so you have something more efficient than just trying all possibilities. Instead, the number of possibilities of such path, where you try all possible drawings, all possible paths in this graph, will grow exponentially with the number of nodes. Instead, this algorithm just grows with the number of edges, which is polynomial in the number of nodes. Okay, it's at worst n squared, where n is the number of nodes. So you have an efficient algorithm. So this is an easy problem. This is what we mean in computer science by easy. So yeah, just a quick remark. Now, two of these two bridge. This one has been changed to that location today, and this was one removed. So the problem has changed, the map has changed, and now there is an Eulerian path in the new problem in 2020. So now let's look at a slightly different version of the problem that looks very similar, but that is fundamentally different. It's called the Hamiltonian path problem, which asks the following: can we find a path that encounter each node a single time? Before it was every edge a single time. So you see, we slightly changed the question, but the problem is very different. So today, to the best of our knowledge, the best solution is just to try all possible paths. There is no efficient way to answer that question for a given graph other than just trying. Okay, and of course trying takes an exponential time, because there are exponentially many ways to try to find path. Okay, and of course exponentials grow extremely fast. So even if you have a number of nodes which is 30, you would have to try a number of paths which is of the order of 10,000s of billions. So let's say if the number of nodes is around 50, if you want to try them all on a supercomputer, it would take more than the age of the universe. So this slight variation of the Eulerian problem, which is easily solvable, instead this variation is not solvable easily. Okay, so this is a hard problem. Okay, even if they look very similar. So this is what I meant by it's not easy to know in advance whether a problem is hard or not. Okay, that's why it's such a deep and important question also. So we have these two problems. One is very easy, the other is very hard. Okay, so in computer science, when a problem is easy like this and you can check, you can find solutions with a number of operations that scales polynomially with the number of nodes. In the graph formulation of the problem, it belongs to so-called P class, P for polynomial. These type of problems where we cannot find a better way than just trying all possibilities, we cannot be smart. These type of problems are called NP complete. So NP means non-polynomial in the sense that we don't know a polynomial procedure to find a solution. However, if I tell you this is a solution, you can check easily. It takes a very short amount of time to at least check that a solution is indeed a solution or not. And these are called complete. So not all hard problems are complete, but this Hamiltonian path problem is complete in the sense that you can prove using what we call reduction techniques. This is a whole field in theoretical computer science, that somehow if you can give me an efficient algorithm to solve this problem, which we don't know, but you can at least prove that if such an algorithm exists, then with the same algorithm you could solve a very, very, very large class of other hard problems. So somehow they are all connected. They're just variations of a kind of big problem which encompasses them all. Okay. I haven't said it, but you can stop me anytime, of course, if there is any question. Yes, so if you solve one, you solve them all, and actually if someone can prove that, so if you can give me an algorithm that solves such a problem, you will become rich, because there is the Clay Institute in the USA that would give you $1 million, and they would also give you $1 million if you can prove that there is no efficient method to do so, to really prove that easy problems are, so the P problems are really a different class than the NP problems. So this is one of the most fundamental questions in computer science and also in statistical physics, but are there truly hard problems, or is it that we're just not smart enough? So today it is believed that there are truly hard problems, but there is no proof, because it's very hard to show that a problem is truly hard, because proving that something is easy is possible. You just need to exhibit an algorithm that solves the problem. Showing that something cannot be solved, how do you do that? So it means showing that all algorithms, including those that you do not know, cannot work, which is much harder, of course. Okay, so that's why this problem is an open problem. So now, how does it connect to statistical mechanics? So, of course, what I showed to you is that some problems are hard, like these NP-complete problems that can be hard in general, but of course you can generate instances of graphs and ask the same question, the same problem, and in this case it's very easy to solve. So let me draw this graph, and I ask you, can you find a path that passes through all the nodes a single time? And the answer is trivially yes, because there is only one path. So you see, of course, whether a problem is hard or not depend on the instance of the problem. So we have two extremes. We have some instances that can be very hard, some instances that can be very easy. So it probably means that there is a whole spectrum of hardness levels, if you want. And so the question is, can we understand what the spectrum is? And is it the case that there is a continuum of levels of hardness? Are there some problems very easy, then slightly less easy, medium easy, slightly hard, then very hard? Or is it that we go from very easy problems to very hard problem in a sharp way? These are two possible scenarios. And this is where statistical physics enters into play. So what StatPhys wants to understand, and what is basically define an ensemble of instances for a given problem, and ensembles of graphs, and try to understand for realizations of these random graphs whether problems are hard or not. Okay, so is a problem typically hard or typically easy? Okay, and so yes, something must happen between the very easy problems and the very hard problems. Okay, and the transition between these two classes is usually sharp. It's not a kind of continuum of easy to hard. It's usually sharp. You go from very easy to very hard. Like in the spike-Wigner model, you remember in the phase diagram, the error of the best known algorithm was as bad as it can be as a function of the signal-to-noise ratio, which defines a kind of ensemble of problems. For every signal-to-noise ratio, you have a different problem. So the error was as bad as possible, and suddenly it was good. Okay, and it was optimal actually, and so the transition was sharp, and this is often what happens in this problem. And the transition between the two, of course, is a phase transition. Okay. So let me discuss another combinatorial optimization problem, which is called coloring, which is another instance of an NP-complete problem. So in the coloring problem, which is again one of the ancestors of graph theory, because it was a very important and concrete applied problem people were trying to solve a long time ago, is the following. I give you a map, and I ask you, can you color the map in a way that two countries that share a border have a different color? With only 3 or 4 or 5 colors. What's the minimal number of colors you need? Okay, and actually for maps like this, 4 colors are enough. So this is a theorem. It was conjectured a long time ago. Then the proof took more than 100 years to be obtained. So it looks like a simple statement once you try, but actually it's a very deep result. only 4 colors are enough to color a map. And an algorithm to do it efficiently, actually, it looks like once you know that 4 colors are enough, it should be easy to do, but it's not the case. It took additional 20 years to get an efficient algorithms to do it for general maps, of course. Okay, so again, you can write down this as a problem on a graph. You associate a node to every country, then you connect with an edge if they share a border, and you have your graph. And so the theorem tells that 4 colors are enough to color any planar graph. So a planar graph means a graph like this where no edges cross. Okay, and you can always map a planar graph onto an actual map. Okay, so it's a graph that you can draw on a plane, on a sheet of paper, such that the edges do not cross. Okay, and the properly colored graph is, of course, a choice of colors for this node such that adjacent nodes are of a different color. Okay, now let's make the problem more interesting. Okay, now we know what happens for planar graphs. Let's consider more generic classes of graphs, so more generic instances of the same problem. Okay, this is where the notion of ensemble of problems of instances appear. And one way to define an ensemble of instances is by studying notions of random graphs. So we're going to associate a probability distribution to graphs, draw these graphs according to this probability distribution, and try to understand what is the hardness of coloring graphs depending on this probability distribution. Again, this probability distribution can be tuned by some control parameter, let's say the average degree of the nodes. And as a function of the average degree of the nodes, is the problem easy or hard is the graph easy or hard to color, okay, for an algorithm. So these are examples of random graphs, which are actually free colorable. So 3 colors are enough, but in general, you may need more colors. Okay. And so now, using methods from statistical physics, like actually the replica method that we studied in this course, you can draw the phase diagram of the problem. Like we have drawn the phase diagram for the spike-Wigner model, you can do it for this combinatorial optimization problem in a very similar fashion. So here is the phase diagram. So the control parameter, which used to be the signal-to-noise ratio in our problem, is here played by the density of edges. So it's the number of edges is L. The number of nodes is n, and c is L over n. Okay, so the more you have edges in the graph, the bigger is the c. The more you have edges compared to the number of nodes, the bigger is c, right? Up to a factor of 2. Okay, so basically what we do in these experiments is that we draw for any given value of c, you draw a very large number of random graphs with this average density of edges, where every node is kind of connected randomly to the others, such that the average degree is fixed to be c. Okay, and then you take your best algorithm and you try to solve the problem. Okay, and what will happen is the following: the fraction of random graphs drawn according to the distribution at fixed c that you can color will be 1, and then suddenly you have a drop, and then it goes to 0, and you see that this transition becomes more and more sharp as the system size increases. For 50 is in blue, for 100 is in red, becomes more sharp. And with the replica method, you can predict that this becomes really a discontinuous transition at a precise value that matches the experiments. And so you have a discontinuous phase transition. So it means that you go from basically graphs that are easy to color. They can, almost all of them can be colored in this region. So it's a colorable phase, to a non-colorable phase where almost all the graphs, you cannot color them properly. You will always make mistakes. Okay. Now, if you test the performance of the best known algorithm to find these colorings, these are the dashed lines. So you track the computation on time in this is some unit of time. You see when the system size is 50, you see some bump here around the transition, and then it goes down. And the bump become more and more pronounced as the system size increase. And actually, the bump here becomes exponentially pronounced in the number of operations you will need will grow exponentially with the number of nodes. And this is the onset of hardness. The problem is actually very hard to solve close to the transition, because this is the region where you have these long-range dependencies emerging between the nodes, in the sense that if you change the color of a single node for a graph with that average connectivity somewhere around here, it will have an influence on all the nodes in the graph. Essentially, you will have to basically flip a fraction of the nodes remain in the graph, even those that are very far away. You have these long-range dependencies that make the problem difficult. Instead, here, most of the nodes are disconnected or connected to few of them, so it's easy to find the colorings. And deep here, there, most nodes have a very high degree, so it's very easy to quickly say that you cannot color the node. Okay, but only close to the transition, the instances are truly hard due to these statistical dependencies. Okay. Okay. Yeah. So we're happy. This is really a phase transition. Okay. So you recognize this, like I told you, this phase diagram that we observed in the Spike-Wigner model. Here, where we had a statistically impossible inference regime, a hard regime, and then an easy regime for inference. Here we have something similar. We have an easy regime for colorings at low connectivities. We have a hard regime, and then we have a regime where it's impossible. The graphs, the probability to find a graph that is colorable is 0. So it's impossible. Okay. And this is the only region where free colorings exist. So around half of the graph are colorable and the other half no. But it's very hard to say so. Whether if I give you a graph with this average connectivity, it will take a very, very long time to or find the coloring or tell me, no, I've exhausted all possibilities and I could not find one. Okay. And of course, I mean, of course, not. This is far from obvious. The physics of these hard phases, I mean, this kind of phase diagrams are deeply connected to physics. Of course, you can think of this easy coloring region or the easy phase in inference problem as a kind of liquid phase, where basically the particles in a liquid are interacting just locally somehow. There is no long-range correlations with particles that are far apart in the liquid, and this induces. So you can think of. I mean, at the algorithmic level, this induces simplifications. Not having long-range correlations imply algorithmically easy problems. Close to the hard phase, the problem behaves more as a glass. Okay, and in a glass, you have these very long-range correlations between the molecules and the atoms in a glass. Okay. So now let's. So are there questions? I don't know if there were hands raised or any questions in the chat.
Any questions from audience?
Don't hesitate to stop me. So now I would like to show you additional examples. Yeah, sorry, there is one.
Yeah, myself, Tushar. I have one question.
Yes.
Actually, in that computer programming, I heard that means computer genocide means theorem genocide is applicable. Means in US, so many computer systems, supercomputer or whatever the latest quantum computing, theorem genocides concept is there. Means if you organize one program in supercomputer or quantum computer with the help of physics theorem, then another theorems are genocide that program. So means it's happen due to physical theorem. Means whatever the theorems available.
Can you repeat the concept you're saying? I'm not sure I hear properly. Just repeat the. You're
Actually,
saying.
my question. Yes, my question is. Hello.
Yeah, I'm listening.
Yes, my question is actually in computer system, and so whatever the supercomputer or whatever the new quantum theory, theoretical computers, there is the so many programming is going using the physical theorem, means that physical or statistical theorems using. So
Yeah.
there is the black side is also there. There is genocide, means if you design one program and another program are means oversighted that program. And so it's called genocide of the programs.
I've
Is
never
it
heard
happen?
about this. I never heard
Okay.
about this. But if you send me this on the chat, I will check. Then maybe I can answer your question later. I will check. I've never heard this term. I'm sorry.
Okay. Thank you.
Okay, so now let's go towards another field, which is actually the one we've been studying in this course, which is statistical inference. That is finding the hidden signal in the noise. Okay, so I think some of you know well communications, but let me redefine the problem and then explain the connection. So how do phase transitions appear in communication? So communication problem is very simple. You have an emitter and a receiver that try to exchange some message. But of course, the channel is noisy. So parts of the information that is transmitted is corrupted by noise, and so the problem is at the receiver side to find back this information. So one way, of course, the way to communicate and combat the noise, to try to beat the effect of the noise, is repetitions. It's adding redundancy in the message that is transmitted to fight against noise. So Claude Shannon, that we mentioned a lot in this lecture, is here and understood that there is a limit to communication. If there is not enough repetitions, redundancy in the bits that are transmitted, information will necessarily be lost. Okay, and if you want the ratio between the number of actual information bits you want to transmit and the number of bits that you need to send through the channel, including those repetitions, the ratio between these two is called the communication rate. Okay, and if this communication rate is too high, of course, information will be lost. So you have an emitter, a receiver, a noisy channel, but this information, yes, is corrupted by the noise. Okay, you have interferences. You will receive something which is noised. One model, for example, of noise is called the binary eraser channel. It's the simplest possible model where, with probability 1 minus p, the bits are perfectly transmitted. 0 goes to a 0, 1 to 1, and with probability p, a bit is erased. So at the receiver side, you receive nothing. So it randomly erases a fraction p of the bits. So the simplest way to communicate is really to literally just repeat the message. The simplest type of redundancy is truly repetition. So we call that a repetition code. You take your bits, let's say that 001 represents hello, and you just repeat it 3 times, okay? And indeed, when you are in a crowd or where you are at the phone and someone does not understand you, you simply repeat until the person gets the message. In this case, the rate is a third. Why? Because for every bit that you want to transmit, let's say the first 0, you had to repeat it 3 times. So you need to pay the price of sending 3 bits to communicate only 1 of information. So the rate is 1 over the redundancy is a third. It's the number of information bit divided by the number of transmitted ones. Okay. And what Shannon has proved in 1948 is that basically whatever code you're using to try to add redundancy in order to fight the noise, even if you're trying to use smarter things than just repeating, much smarter things, you cannot beat a certain communication rate. You cannot be beyond the communication rate. So this figure is telling you, assume that you allow yourself a certain error rate at the decoding side. So you allow yourself to lose, in average, let's say, one bit for every 10 to the 10 bits communicated. So it's a very small error, right? It's less than a billionth of the bit must be communicated correctly. So you put a line there and you ask, what is the maximum communication rate that I can attain? So what is essentially the minimal redundancy that I can allow myself to reach such a error? Shannon has proved that it's given by this curve here, by this wall. If you allow yourself 0 error, let's say 10, this is 0, then there is a maximum communication rate, okay? So there are 2 surprises here. And by the way, the communication, the repetition code we were talking about, where you repeat just 3 times, is there, okay? So the error will be of order 10 minus 2, of order 10 minus 3, of course, because in average you will lose 1 bit. If the probability of error of eraser is 10%, this repetition code with a third rate will attain a certain error which is there, okay, and a third is here. R3 is here. This is this line. This is the communication rate of a third. With a third rate, you can attain an error which is somewhere there, okay? So you can go from 10% of the bits erased to something like half of this, okay? And of course, the more you repeat, this is R5, where you repeat 5 times, the more you can decrease the probability of losing bits, the fraction of bits that will be erased, okay? And if you repeat infinitely many times, 61 times, you can make this error very, very, very small, of course, okay? So Shannon has shown that, first, perfect communication is possible, which is a surprise. It's the first surprise. Even if 10% of the bits that are transmitted will be erased, you can still find a way to communicate, to add redundancy in these bits, such that at the receiver side, you will make no error. Okay, so this is the first amazing fact. And the second amazing fact is that given a certain error rate, you cannot communicate more than at a certain rate. And this is called the Shannon capacity of the channel. And so this is really like a phase diagram in physics. So there is a region where communication is possible. This is a phase diagram as a function. It's error rate as a function of the communication rate. It's like a temperature and pressure in physics, if you want. These are 2 control parameters. And you have these 2 phases where you have a possible communication region and an impossible communication region, okay? Perfect. And what happens in between is the phase transition. Perfect. So Shannon told us that whatever you do, and if you had access to the most advanced technology that will ever exist, you will never be able to communicate at a rate exceeding the capacity of the noisy channel. There is a fundamental phase transition that prevents you to do so, okay? Perfect. So now let me discuss a very fascinating phenomenon which really links even more communication and signal processing with physics. Okay, and this phenomenon is called nucleation. So it goes like this. So the question is, so repetition codes, which are very stupid codes, you just repeat the bits, can attain this. This for a given error, you can attain this communication rate, which is pretty bad. It's very far from the fundamental limits that Shannon found. One remark is that Shannon has proven that this is the best you can do in terms of communication rate at a given error, but he never gave an algorithm to reach this performance, in the sense that you didn't explain us how to code the information, how to properly add redundancy. This is the coding part. And secondly, given this unknown code, you would need at the receiver side an efficient decoding method. So given the observation of the noisy bits with the errors, how do you recover the original ones? This is the decoding problem. You need to solve both problems, and Shannon didn't. He just told us you cannot do better than this, which is quite amazing if you think about it. Being able to give a results for all algorithms without studying any is kind of quite amazing. So when there are kind of hard problems like this, nature has found a way to solve these hard problems in a sense. And this is called nucleation. And so this is more than an analogy. You will see that we use this in signal processing, in coding, everywhere. So this is super cool water. So if I click, so you see this is liquid water, which was actually below 0 degrees Celsius, much below. Let's say at minus 30 degrees Celsius, you put in the fridge for a long time. And if the water is sufficiently pure, what you would realize, quite amazingly, is that it will remain liquid in the fridge, even if it's below zero. But now if you perturb slightly this water, let's say with a punch, or if you put an impurity in it, you will see a kind of crystal appearing, ice, and then this ice will propagate like a wave, like this, starting from the nucleus, from the point where the perturbation occurred. You see really this wave here propagating. So the water crystallized suddenly in this kind of wave propagation, with this wave propagation. And the reason is that if you see, if you start, so this is again the free energy picture. Let's say you are above 0 degrees Celsius. So the minimum of the free energy is the liquid state. But if you slowly lower down the temperature, what will happen is that you will have this other minimum in the free energy that will appear until the equilibrium is the solid. But your system is kind of blocked in the liquid state because there is a barrier between these two states. There is, it would take quite some time if you want to jump around this barrier. Even if there are more, it's more favorable from the physical point of view, from the energetic and entropic perspective, to be solid at this temperature. It would take some help to reach that state here from the liquid one. Okay, so this is called super cool water. And the way nature solves this problem is by nucleation, in the sense that if there is any small perturbation in the system, mechanic or impurities, somehow it is enough to crystallize locally, and then once you crystallize locally, it propagates like this. It has to propagate, okay? And the reason this happens is that the system is has a kind of notion of dimensionality. It's not a mean field system like what we studied in the course. Like every variable in this water, every molecule, only sees its local neighborhood. There is a notion of local neighborhood. While the problem that we study in the course, like the spike-Wiener model, the variables have no neighborhood. If you draw the factor graph, as we did this morning for this problem, every variable interacts with all the other ones. There is no notion of local neighborhood, okay? And this prevents, in particular, this kind of nucleation to happen. So what you can do is to change the problem, and let's say now we go towards go back to communication. We would like to exploit this nucleation phenomenon, and this is what modern error correcting codes are doing. It's called spatial coupling. So let me give you the idea. A way to code information is using what we call parity checks. There is a type of code which are called low density parity check codes, and they work in the following way. What you do is that the emitter that wants to send a message and the receiver, they kind of agree in advance on a big set of allowed sequences. These are the possible messages to transmit. And of course, if the number of sequences to transmit is big enough, you can map any words to one of these sequences. So you can transmit any information if you wish, if the alphabet is big enough, okay? So the way to agree in advance on this sequence, to construct this dictionary, is by using what we call parity constraints or parity checks. So basically, you only allow sequences of bits such that some selected sums of these bits have to be an even number. Okay, so this you can represent this as a factor graph where the factors are connected to these nodes representing the bits to transmit. And if a factor is connected to some nodes, it must be that the sum of these nodes is an even number. So it allows to spread the information, to couple, to correlate these bits. So now imagine that you have constructed your code in a kind of chain like this. So you put the bits in line, and you connect them with parity checks in this kind of structured manner. You see that the first bit, let's say, is always connected to an individual check. So it means that the first bit will always be a 0, okay? Because the sum of the neighbors of this guy must be a 0. There is only one, so it must be even, so it must be a 0. So even if it was erased from during communication, if you receive a question mark here, it was erased, you know in advance it was a 0 because you pre-agreed that it was a 0. So you already know this. But now that this bit has been reconstructed, due to this parity check there, this one can be reconstructed because you see it's connected to this one that you actually observed, plus this one that you just reconstructed. So it allows to reconstruct that additional bit. But this one is connected somehow to this one that was erased also. So it allows you to check that the sum of this one plus this one plus this one must be even. 1 plus 1 is 2. It's already even. So this must be a 0. And indeed it is, etc. So you see that you have a kind of decoding wave that happens starting from this kind of nucleus that we call also the seed, which is kind of the piece of information that you always agreed between the receiver and the decoder to send. It's always the same 0 that you send at the beginning. And it allows to decode starting from there in a kind of ordered fashion. Okay? And if you use this strategy, it works amazingly well. So here, I've used this strategy to decode bits representing an image. So it's not just bits, it's not just 0 and 1s. It corresponds instead to the values of gray pixels. So the value can be anything between 0 for black to let's say 200 for white, and any value in the between is a different level of gray. They are like bits, okay? And I've transmitted these bits through a noisy channel. What I received is what you see at the beginning. At the beginning, it's very noisy, and I'm trying to recover the image, okay? It's like a communication problem. And I've implemented a coding strategy of this sort. And if I order the pixels in the correct manner, I would see that there is a chain of dependencies between the bits there. And you see that the reconstruction error using an algorithm, it starts from the first bits which are reconstructed. This index is representing the bits in a kind of the right ordering. And you see a reconstruction wave that propagates from the seed and that propagates in the system, exactly like the seed of crystal propagates in this liquid water. It's the exact same phenomenon. So you can exploit this nucleation strategy that is present in nature as a way to achieve very high inference performance in signal processing or in communication. And if you do so in coding, you can actually design coding schemes that can reliably transmit information through a noisy channel up to the Shannon capacity. You can close that gap. So in the language of what we've done in the course, you remove the hard phase. Somehow it disappears. There is no more hard phase. Okay? Okay. I like this quote by Richard Feynman, who got the Nobel Prize in Physics in 1965. That connects, he understood directly, of course, that statistical mechanics, which is the mother of thermodynamics, or vice versa. Historically, thermodynamics appeared before, but statistical mechanics explains it. He understood the links with information theory. He said the science of thermodynamics began with an analysis by the great engineer Sadi Carnot of the problem of how to build the best and most efficient engine, and this constitutes one of the few famous cases in which engineering has contributed to fundamental physical theory. Another example that comes to my mind is the more recent analysis of information theory by Claude Shannon. These two analyses, incidentally, turn out to be closely related. And of course, they're actually two sides of the same coin. Statistical physics and information theory are very, very close cousins. I'm just checking if there's no question. I'm already beyond time. Do you want me to take additional 10 minutes to finish, or do you want me to finish now?
We can take 10 if you wish, yes.
Okay, so I will do so. Let me give another example of an interesting inference problem that I mentioned at the beginning of the course, which is community detection. So in this problem, you observe a graph, okay? So a graph like this that looks random, but actually it's not random. There are communities hidden in it, in the sense that there are some groups of nodes which are more connected to each other than with the rest, okay? So let's say this is the group of interactions of friendships between on Facebook. A node is connected to another one if they're friends on their network. And the task would be to infer back who is voting for who. Actually, these kind of techniques were used to bias the American elections during some years ago. There's been this scandal with Cambridge Analytica that was used by one of the two parties. I will not say which one, to try to bias people in voting in one or the other direction by targeting them. And so the first thing you need to understand is who is a priori voting which party. So this is this community detection problem. You have this is the data, this random noisy graph, and you want to infer the two communities, the blues and the red. Okay, and yeah. This is a hard problem, and another equivalent way to see the problem, by the way, it's exactly the same thing, is that I give you an adjacency matrix, which looks like this. This is the adjacency matrix of this graph. So there is a one, so rows and columns are indexing the nodes, and I put a 1 in this matrix if they are connected in the graph, okay? And so I give you a random permutation of this adjacency matrix, and you're trying to find what is the right permutations of the columns and rows, such that you exhibit this community structure. You see that nodes in this block are more connected together than they are connected with the other nodes, and these are the other group. So it's about finding the right permutation, and of course the number of permutations is is even more than exponential. It's n factorial, where n is the number of nodes. So it's super exponential. Okay, so it's a very large number of possibilities to try. And the phase diagram of this community detection problem, as I told you at some point in the course, is actually the one of the Spike-Bigner model. If you define the things correctly, and what we called the signal-to-noise ratio in the Spike-Bigner model, the lambda, plays the role in the community detection problem of the relative probability of intra-community connection. So what do I mean by this? If lambda is 1, it means that a node in the graph that belongs to that is red has the same chance to be connected to another red node or to a blue node. And it means that the graph is completely random. Okay, there is no information about the communities. If instead this is different than 1, it means that you are more connected to, it's greater than 1, you are more connected to nodes in your group. So there is information in the graph. Okay, and the other parameter would be the fraction of nodes you reconstruct. And this phase diagram, which is the very same as we discussed in the Spike-Bigner model, is understood for community detection through the analysis of the Spike-Bigner model. And in particular, for example, to detect these communities, you can do a spectral algorithm, you can do PCA that we analyzed, and what you realize is that the top eigenvector of the adjacency matrix of the graph will give you information about these two communities. Some of the components will be more positive, some other more negative, and you can read the communities in this way, at least get an estimator for it, which is not perfect, but this top eigenvector contains information about the node states. Okay, but you can do something smarter, which is based on this AMP algorithm we discussed, the Bayesian algorithm. Okay, last example, machine learning. So the classical problem in machine learning is supervised learning. You have many others, but it's about learning from examples. So imagine that you have a big data set of labeled data. So you have images of dogs and cats, and they come with their label: dog, cat, etc. And you try to write down a program, an algorithm which is predictive. So you want that when fed with this data, it is able to correctly match these labels with these images. And in particular, you want that if you then feed your algorithm, your model with a new input, which does not come with a label, it will output the correct label. Okay? Yes, this is what I mean by this. Unlabeled data, you want it to spit out the correct answer. This is the supervised learning problem. So if I give you a certain number of data, you can use simple strategies to try to classify, to find a boundary decision. So this kind of two-dimensional space represents in reality the very high-dimensional space of images, whose dimension is the number of pixels, so it's tens of thousands. But here I can only show you things in 2 dimensions, of course. But you should imagine all these images as a point living in a 10,000 dimensional space representing the images. And each of these points comes with a color, a label. So there are the dog points and the cat points. And you're trying to find a boundary decision between the two that separate the two classes. Okay, the more you have example, the more you can fine-tune this boundary decision, of course, until hopefully you find something which is predictive enough. Okay. Perfect. So this simple classifier is an example of the very simplest neural network you can think of. It's called the perceptron, or just a linear classifier. Basically, it takes as input an image, which are the values of the pixels. It will multiply this vector by a set of weights, and then it will apply a nonlinearity and spit a sign, dog or cat, plus or minus 1. So mathematically, you are taking an input, which is X, which you can vectorize this image if you want. You're taking the dot product with a vector, which represents these weights here, and then you're taking the sign, okay? Perfect, and you can analyze the performance of such a model on a simple setting where, of course, the images are not dogs and cats, but you have some mathematical model for these images. They are kind of Gaussian vectors with there are two Gaussian clouds. Okay, it's like a Gaussian mixture, and you can compute using the replica method that we studied in the very same way. It was done in the 80s. The generalization performance of such a linear classifier. Okay, so once it has been trained given a certain amount of training data, this is the control parameter, like the signal-to-noise ratio. You can track the order parameter, which is the generalization performance, the performance on unseen data that was not part of the training data. How good is the model at labeling unlabeled data? And what you see is that, again, you have a region where the optimal classifier like this has a bad generalization error, it's high, and then suddenly you have a sharp phase transition, and then it's zero. It means that you have found the perfect line that separates the two classes, okay? But you need enough data to do so. And this is really a phase transition again, okay? You see it's sharp, suddenly you can generalize perfectly. Now, if you try algorithms to find this boundary, this classification, boundary, the true theta, you see that you need more data to find it. So efficient algorithms are these dots or this green line. And so the learning becomes easy only when you have more data that what information theory predicts. Information theory tells you that you should be able to perfectly generalize given that amount of data, but you don't know any algorithm able to do so. So this is a hard learning region, and then suddenly the learning becomes easy. Okay, so it's exactly the same picture. So that's it. I hope I convinced you that the methods that we've studied in this course can be used in plethora of other contexts, and all this can be unified actually through the language of information theory and statistical physics. And so I hope that it had triggered your interest enough so that you can take a look by yourself for applications of interest. And that's it. I will stop there.
Yes.
So if there are any questions, I'm happy. If some of you are curious, I can send the slides. I'm happy to share this.
Yes, sir, please. So, if we do not have any questions, I would like to express a vote of thanks, mentioning a big thanks to Dr. John Barbier, who has kindly accepted our proposal of doing GIAN course with us. Sir, we are so grateful that you attended and presented a different dimension of connecting computer science problems with information theory, statistical physics. We really never had this idea that we can also follow these frameworks. I myself has learned a lot, and then I
Thank
would
you.
like to mention, thank you, sir. I would like to mention the great support by our director, sir, Professor Vinod Kumar Kanodia, who has provided all the necessary support to conduct this GIAN course. And then I would like to mention GIAN National Coordinator, to sanctioned and accepted, who accepted our GIAN course grant. And as everyone knows, previously we were trying to have Professor John Barbier here with us so that we can connect and grow and learn and evolve with each other, but that couldn't be possible. So we would definitely be connecting with you, sir, again sometime to have you here in India so that we can learn. Then I would like to mention a gratitude to our GIAN coordinator from NIT Jalandhar, Dr. Vimal Bhardwaj, who has always guided us and supported us for any things to be done, for all the procedures and protocols to be done, how to be conducted, and I have always taken help. And then I would like to mention my another course coordinator, Dr. Deepthi Kakkad, has always provided all the fruitful thoughts thoughts, ideas, and she is the only one who motivated me to do this course. I just went her telling her that I went ICTP. She told me you must propose a GIAN course. This is the kind of thing we can do, and it can really help our students. I was never introduced, so a big thanks to Dr. Deepti ma'am who introduced this course to me, and then another thanks to Dr. John Barbier who kindly accepted to do this GIAN course with us. Then I would like to mention our head of departments IT, Dr. Vijay Chahar, head of department EC, Dr. Ashish Raman, who have always provided their kindly support and infrastructure required to perform this entire course successfully. And definitely not the last, the most important, I would like to mention all my participants who have attended, especially Dr. Julio, despite of having time lags from US. Dr. Julio has attended most of the sessions. Thank
Well
you,
done.
Dr. Julio.
Yeah,
I would
thank
like to
you. No, it was
mention,
very interesting, so it's worth it.
Thanks.
I remember we connected in Youth in High Dimension in ICTP Italy, right?
Yes.
So I
Yes.
hope, yes, we will be doing some more things great together. And then I would like to mention all the professors who have kindly accepted our course to join by looking at the importance and significance of the course, especially Professor Divya Bansal. Despite of her busy schedules, she decided to join us. Thank you, ma'am, for joining our course. Then I would like to mention Then I would like to mention Professor Shekhar Verma from Triple IT Allahabad and Dr. Arpita, Dr. Aarti, Dr. Tanu, Dr. Satnam, Dr. Amanpreet, all of my students, Fiza, Abhishek, Gagandeep, Amrit Raj, then Tushar, Sonali, I have no names. Some of them have been texting me. I couldn't attend this talk. I had some engagements. Then I have been sending them the notes and the required things to do. And so I believe that this course will really be fruitful to our postgrad and PhD students, and especially for research purposes. We would definitely be connecting with you for more queries, maybe about writing projects together, and then taking idea how can we connect our computer science problems with the concept of mean field theory of Bayesian inference. So this is another dimension you have introduced to us. So with all
Thank
these
you.
words, I think words are not enough to express my thanks to you. So if this thing to say anything.
No, I am.
We are very thankful.
Go
We are
ahead.
very thankful. We extend our heartfelt thanks to your invaluable insights. And your expertise has greatly enriched our understanding. It was truly privileged to learn from your user, and keep stay in touch and continue this academic connection.
Okay, I am very. It
Thank
was
you.
really a pleasure to give the course, and of course, I'm happy to engage in any discussion with the students, with anyone who wants to know more, and so don't hesitate to share your thoughts and send me a mails, and I will take the time to answer and clarify any things you would like to delve into a bit more.
Thanks a
Thanks
lot.
a lot. So goodbye,
Professor
everyone.
Divya, if you would like to say something.
Glad, I attended this course. It was definitely very mathematical, very intensive, very deep. Did take us a while, to get a feel out of it, but eventually, with the kind of applications which were explained and with a little more notes and searching here and there, finally, we could really make it. And a lot of my PhD scholars were also attending from my lab, and my faculty was also attending. So it was like we had the entire research group was here. So the good thing is that we could discuss with each other, and now we are the entire team, 4 or 5 of us who have attended this course. So it was absolutely wonderful attending this course, and thank you to Jaspal and Dr. Deepti, for extending this opportunity to our institution, and thank you, Professor Jean. I hope that we'll also be able to collaborate on more projects and more research later.
Thanks very much. It's very kind.
Okay. Dr. Julio,
So
you would like to say a few words if okay, Dr. John Barbe is saying something. Yes, sir, please.
no, I mean, I just want no, I mean, no, I wanted to thank everyone for these very kind words, and I want to acknowledge that I know that it was intense, and also I want to express the fact that it was difficult for me to gauge also the level of everyone's. That there was a very big variance in backgrounds and knowledge. I've tried to find the right balance. It's not easy also because it's this field is extremely interdisciplinary and mixes language and concepts from very various fields. I hope you gain something out of it. It was really nice for me to teach that. And again, 1 week was pretty short and dense for all this, but I hope that at least it have triggered some interest, and you have the right amount of seed of nucleus in this field to start reading papers in your own, and any question in this you can just send me, and I'm happy to Zoom to discuss anything, any question you may have. Thanks a lot. And thanks Jaspal in
Thank you, sir.
particular was my direct contact. Yeah.
Definitely, definitely. Dr. Julio, would you like to express how was your experience to be with us?
Oh,
Don't
I don't know. I'm a man of few words usually, but I think it was good. Like I said, it was very early in the morning, so it's a little bit more challenging, but it was very useful. A lot of information.
Thank you.
Good.
Definitely, next time we will keep US time zone also with us. We took care of Italy time zone. I think with Professor John, I will discuss with other time zones as well while proposing such courses in future so that we can have a common time to attend. So, any of my student, Fiza, Tushar, Gagandeep, if any of you would like to say a few words, or any participant would like to express
I don't
or any
not
other
everyone.
faculty member. Dr. Avni is there from my department. Dr. Vijay sir, HOD of our IT department, is also with us. Sir, would you like to say something, or ma'am, or anyone?
Don't feel obliged. Really, I mean, I think
Okay,
I got a
okay,
lot
sir.
of.
Thank you, thank you. So I know you have a meeting after this, so I will not take much time. I thank you, everyone. So with this note, definitely we will stay in touch and we will grow together. So if we had any opportunity to connect, to work together, we would definitely be doing so. Thank you, sir.
Yes.
Thank you, everyone,
Yes.
for their
Goodbye,
kind
everyone.
Thank
patience.
you.
Thank
It
you.
was a very
Thank
informative.
you.
Yes, sir. Thank you, sir.
Thanks very much.
Thank
Goodbye,
you.
everyone. Yeah.
Thank you.
Goodbye.
Thank you so
Goodbye.
much.
Thank you.
Thank you so much.
Thank you, everyone.
you.